Welcome to the Eduonics Introduction to Scala course. Let's just take a moment to introduce the course. This is the course syllabus which you can find in the documentation for the course, and it outlines the sections and the particular topics that we will work through. But what we'll do now is we will just step through the higher level concepts that the course contains. We will look at why Scala is a language worth learning. What makes Scala different from the other functional languages like Clojure or Groovy? What functional languages like Clojure or Groovy have in common with Scala is they all run inside what's known as the Java virtual machine. If you are an experienced Java developer, then you understand the Java virtual machine very well. But if you are new to programming and you're choosing Scala as your first programming language, then you need to understand you will create better Scala code when you understand how your Scala application interacts at runtime with the Java virtual machine. When we work with Scala, like Groovy, it has a very accessible syntax. We will look closely at the syntaxes for working with Scala types, Scala object-oriented code, and Scala functional code. While we focus on a thorough understanding of the syntax as relates to these types, objects, and functions, we will also delve into the semantics of the Scala type system, how Scala is an object-oriented language at the same time as Scala is a functional language. We will look closely at Scala concurrency and the Akka framework, a concurrency system in Scala used to implement the actor model for concurrent applications. We will look at the interaction between the Akka framework, Scala concurrency, and what is known as the Java memory model employed in the Java virtual machine. This will be a core top-level conceptual component of the course. Next, we will focus on the software engineering perspective of Scala, how we can correctly design Scala applications, how we can employ the appropriate build tools, whether it be SBT or Gradle, to facilitate implementing Scala solutions. We will look at how we can use these build tools to package and deploy our Scala applications. Finally, we will create 3 typical use case Scala applications where we will try and highlight the best practice software engineering design principles. And those principles we will look at are the concept of microservices and modular application design. I hope you enjoy the course. Welcome to the Eduonics Introduction to Scala course. This is Section 1, JVM languages. How is Scala different to languages like Groovy or Clojure? In this course, we're going to run into some confusing words. An example is statically typed. What does statically typed mean? Now I have 3 languages here, Clojure, Groovy, and Scala. Clojure and Scala have been around for a while, but their importance as a programming language is emerging just now, whereas Groovy has been an important programming language for a while. So the chances are that you know some Groovy already, or at least you know some Java. So this confusing thing we're talking about is this statically typed. What does it mean for something to be statically typed? Well, it's good to compare it to a language like Groovy, which is weakly typed. So if we can see easily how Groovy and Scala are different in their type system, that will be a way that we can start to get a good understanding of what is meant when we use the expression statically typed. So here is a project where I've set it up so I can have Java, Scala, and Groovy in the same project. And this is to illustrate that Scala is what we call a JVM language, or a language that runs on the Java virtual machine. So here I have a Java class in a Java package. Here I have some Scala code in a Scala package, and here I have some Groovy code in a Groovy package, all working together. I can call the Scala from Java and I can call the Groovy from Java. Now, if we look at this project layout, so I have a dependencies directory where I have all the Scala libraries, and I've got that to support IntelliJ, and I can use code completion and everything sets up in IntelliJ nicely. Because I'm using this Gradle build file, I don't really need that Scala library because my Gradle build file is supplying the dependencies. You can see that I am pulling in the Scala dependencies here as a Gradle transitive dependency, but IntelliJ needs to find the Scala libraries for its code completion and syntax display. Then I have my top level source package. Then following the convention, I have a main package. Then I have Groovy, Java, and Scala. And here you can see my Groovy types are very similar to my Java types. I have classes and interfaces, but when I look at my Scala code, it's different. So I can just have a file and have as many classes and objects and interfaces and functions in any one file as I like, whereas in Java you have this strict rule, one public class per file. So there's some fundamental differences, and there's my project layout. It's all my dependencies are supported transitively by Gradle. I pull in the Scala library with Gradle, I pull in the Groovy compiler and the Scala compilers with Gradle, and I pull in all the dependencies for Groovy and Scala with Gradle. Now this is a very convenient way to write code because there are a lot of good things that Scala can do, and there are a lot of good things that Groovy can do that I can't do in Java. So by having access to Groovy objects and Scala objects, having these objects and classes and types available in Java greatly increases the scope and power of my Java code. So the JVM languages all work together in a great ecosystem that allows us to write very powerful code. Let's see if we can learn anything from comparing and contrasting the code about the type model, and what do we mean when we say something is weakly typed, or what do we say when something is strongly typed, what do we mean when we say something is statically typed or dynamically typed, as in closure. So let's look at our code. Java is a strongly typed language. So when we create objects in Java, we need to define the type, and this is for the compiler. The compiler goes through, and Java compiler expects strong typing. So it wants to see a type for everything that is an object. We must explicitly declare to the compiler what is the type we are working with. We have a Groovy template object. Here we are in Scala. We have a Scala type. Now let's look at our Groovy. Now here we have a keyword we don't see in Java, def. Now this is how we define a function in Groovy. And here we have two variables. We're not declaring the type of these variables. So this is what we mean by dynamic and weakly typed. So X and Y, the compiler needs to infer them at runtime what they are. Now if we look at Scala, here we see we have definition and value, and we have a third type here we're not showing called var. So Scala has def, val, and var. Now val evaluates as read-only variable, so it's like a static final variable in Java. And we need to declare the type. So in Scala, we have the variable and the type set up like that. So that's very different to Groovy. When we look at the equivalent function in Groovy, because Groovy is a dynamic language, we're not defining the types of these variables. We have this loose or weak typing system, where in Scala, it's a strongly typed language. We must always define the type of a variable. In Scala, def and val mean different things to what they mean in Groovy. Here we are defining a function in Groovy. In Scala, we have a much stronger type system. So our val is for like a read-only or a static final variable. After val, we have var, and these are for variables that can change. They're not like static final, they're like instance variables. And here is how I create the strong type that Scala demands. So here we have an X variable, and we have the colon, and we declare the type. So it's the same syntax here. We create the handle for the variable, then we use the colon to declare the type. After I've declared the strong type for instance variables in Scala, I need to initialize them, or I need to declare the class to be abstract. Now this serves to illustrate how Scala is not a dynamic language by default. It is possible to play with some advanced Scala and give it dynamic behavior, but by default it's statically typed and it's not dynamic. So here I've created an uninitialized var. And you can see the compiler is complaining. It's saying it wants it to be abstract. Now we have entirely the opposite situation in Groovy. Here I'm creating an unbound, uninitialized variable, and the compiler has no problem because Groovy is weakly typed and dynamic, where we have the opposite situation in Scala. If I initialize this variable, I give it some initial value, then the compiler's happy because it's initialized. So everything has to be defined at compile time for Scala. So our statically typed just means we need to define everything for the compiler at compile time. Now, with a weakly typed dynamic language like Groovy, it's entirely the opposite. The compiler is more than happy to infer types at runtime. So that's a good comparison. Now, Java is a strongly typed static language, but it allows us to have instance variables, and the compiler will give them a default value. So we have some fundamental differences in behavior. So we'll just summarize. Scala is strongly typed. I need to declare the types of the variables at compile time. Scala is not dynamic, so everything needs to be initialized. Groovy is the opposite. It's weakly typed, so I just use def or val, and I can infer my values at runtime, so it's dynamic. Whereas Java sits somewhere in the middle. It's strongly typed, but for instance variables, it's prepared to give you default values. So Java will initialize the instance variables for you, but Scala will not. Now that we have a better understanding of what we mean when we say a type model, and we use the expressions strongly typed or statically strongly typed, weakly typed or dynamic, we are in a better position now to understand the object model employed by these JVM languages and our target JVM language, Scala. Java is an object-oriented language, and it's strongly typed. So when we create objects in Java, we declare the type, which we create with a class, and we create an instance of that type with the new keyword. We do the same thing in Scala. Scala is an object-oriented language, so we use a new keyword to create a type which we define with a class. This is an example of a Scala class which we create with the class keyword, just the same as in Java. The only difference is that in a file, this file is called stemplate or Scala template, and the name of the class is Scala class. In Java, when we create a class, as we see here in this main runner, it's defined in a file called mainrunner.java. With Scala, it's completely different. We don't use the public keyword. We have a class with a class name, and the name of the file can be different to the class name, and we could have many classes in the same file. A key difference, we can use val or var for creating our objects. So here we're creating some objects with val. So these are like static final objects, but now I'm creating an object with var. So this is like a variable. It's not static final. This is an object that's meant to be modified, whereas these objects are more like constant objects. Now the def keyword in Scala is reserved purely for functions, and that's what we'll talk about next. Our object model is defined via our type model by the way we create objects and the constraints on those objects as related to the types and the type system of the language. We also have another model that applies to languages like Clojure, Groovy and Scala, and that is their functional model. How do they implement what is known as functional programming? And this is the big plus for Scala, is it's almost 100% a fully functional language at the same time as retaining Java's object orientation. This is how we define a function in Scala. First, we always use the def keyword to define a function. Then we have the handle for the function. This is the name or the identifier for this function, which we can think of as a rule. Then we have the parameters. Now Scala is strongly typed, so we use the type definition. We are using two integers here, so we have the variable and then the type of the variable. This is the syntax for defining a function parameter. Then we must declare the return type of the function, and then we have the body where we implement the function's behavior. When I define a function, I use the def keyword. When I create an object, I use the val or var keyword. Then I use the class to create the object, and I have the identifier or the handle. Now in Scala, you have this object keyword. So here I am creating an object with a class. So this object keyword in Scala means something a bit different, and we'll go into it more later. But for now, you can think of it as defining a static block of code that I can run. Now, what it gets used for here, if we look at a classic Java main class where we have a main method, I can use my object block of code to define a main class. And here I have a main function, and it's following our functional syntax where I use the def keyword, a handle for the function, I create the parameters and define their types. So everything in Scala is an object. So in Java, when we use the void keyword, so here we have the void keyword, in Scala I need an object for what is known as a void, and that's the unit type. So I have a return type. Here it is unit or void, whereas this function will have a return type that is an int. So every function has a return type. If it's a void function, then we use the unit type, which is the object for void, as we find in Java when we use the void keyword. So now we can look at the way these JVM languages, including Scala, implement functional programming. Now, Clojure is different to Scala because Clojure only has very lightweight data modeling. Clojure is not an object-oriented language. It's a purely functional language. It implements behavior purely with functions. Groovy and Scala are very different because they are object-oriented language, and they can implement behavior via their objects, but as well as functions. So we're going to call them object functional. When you have object functional as your functional model, there are some issues that arise to do with state. In a functional program, only the function can change the state, but objects through their behavior can change the state. So there's an important concept inside Scala to do with its object functional model, and that is immutability. And this is what we'll talk about next. In the next topic, we will go through the important and critical issues of writing functional code when you have objects that can change state. Welcome to the Eduonics Introduction to Scala course. This is Section 1, Concurrent Programming and Functional Languages. In this topic, we're going to look at Scala concurrency. In the previous topics, we talked about the need for functional languages arising from the need to write concurrent programming. Java is a concurrent language which has excellent support for managing parallel processes, and its concurrency model is based around a blocking mechanism known as a lock, which locks down objects on threads so they can only be altered by their current thread. That's Java's attempt to maintain state, and because it's based on these locks, it's blocking. Now Scala, that has almost full support for functional programming, and it has an excellent concurrency system known as Akka. Now we previously outlined the case for functional languages as being good for concurrent programming because functions maintain state, and this is the issue when we have many parallel processes. There is a recipe for concurrent programming with functional languages that's based around the concept of immutability, that is, objects that cannot be changed. And we looked at the classic example of a Scala immutable type, which is known as a case class. So we have a constructor where we can pass initialization variables into our case class type. Once we've passed in and initialized our case class type, we can always call for these variables, but we can't set them again. There are no setter methods. So that's what we mean by an immutable type. A case class in Scala is a good example. Here is a simple recipe for how concurrent programming is achieved with functional languages. 1. we have an immutable object to preserve state across many parallel tasks running concurrently. 2. A function acts on an immutable object to prevent unwanted side effects. 3. The system is asynchronous, so it's non-blocking. Any communication between parallel tasks acts in a way so that the callback can come at any time and no task is blocked by the needs of another task. So these are the three core components of a functional language concurrent system. So what we'll do now is we'll move on and we'll look at a simple program to demonstrate how Akka achieves this simple recipe, where Akka is a concurrency framework for Scala. So here we have the entry point for our simple concurrent program in Scala. Now notice in this code we are using our object keyword to define a static code block, but we are not using a main method here. And that's achieved because we extend this Scala class app, which encapsulates the main method. I'm showing it to you here now so that if you see this, you will understand what's going on and you won't be confused with objects that declare a main method as the entry point for the application. On this line, we are declaring a system that is a concurrent system. So we're thinking about these tasks running in parallel. That collection of tasks, we're thinking of it as a system, and it can communicate, and it's an Akka system. It's using the Akka framework. And because it's a top-level object, defines the whole system, we don't really want it to change, so we define it as a final static variable. Then we create a top-level actor that will exist in our actor system. Now when we declare our actor system, in its constructor, it's got rules about what you can use for the identifier, so no leading underscore is allowed and only alphanumeric characters. Using our system type, we create an actor for our system, we give it some input properties, and we give it a unique identifier. And now we can use our actor to send messages. So here we are with our actor that we have defined using a message send operator, sending a message that is defined. That is, the actor is set up to respond and handle this message. It understands this message. But now we're sending it a message that's not really meant for a simple actor, and it is not defined inside the actor. So when it receives this message, it should just do nothing. All these actor messages are flying around, and the one that makes sense for the actor, it can act on, and anything that doesn't make sense, it can just ignore. So it's a very simple system, but effective. Now this is a class where we define the properties for our simple actor. See how this class is coming in through the constructor. This class defines the properties that our simple actor will use when it's interacting inside the actor system. So it has this function receive, which is defined with the function keyword. And in this function, we define the behavior. If you're coming from the Java world, it's important to understand Scala does not implement a switch construct. So this is not like a switch statement, but it acts in a similar way. If the message coming in matches with this case, then we do this behavior. However, if the message is not defined, there is no matching case for the incoming message, then we do our default behavior, which is what we do when the message doesn't make sense for us in our role as a simple actor. Now we will define this underscore syntax. This is a key construct in Scala. The underscore is like a binding slot. So when we are using functions, they act on these predefined immutable objects. But we can be loose in the way that we bind. So here we are binding this case to this message. But here we are binding anything. So if we don't have an actual case that's exact, then we can use this binding case to bind to any message. Now, the reason I mention this is because we will use this a lot in higher order functions and functions that can work on many different types. When we are using functional code, and in particular closure, we bind to different types of variables in different contexts, and so we will often use this underscore syntax in that situation. Now that we've stepped through our Akka code, explaining the important high-level types and the way they interact, let's set this up in our multi-language Scala project and check that it's syntactically correct. So this is the same code set up in our multi-language project, and here you can see concurrent Scala.Scala. The orange or the brown these are the object code blocks, and then we have the classes red section. And you can see we have our Groovy types, a class and interface, a Java class. So this is a very nice way to set up code where you're using multiple Java virtual machine languages together to create an application. Now, to get this code running, first we need to do some work to get the dependencies, and that's where we can turn to Gradle as our transitive dependency manager, and we simply put in the correct syntax in Gradle, so it will go to Maven and pull down all the supporting code that we need for the Akka concurrent system in Scala. So here we have an Akka actor type, and we have the properties and the system. So now with Gradle, as well as the transitive dependency manager, as well as supplying us with our dependencies, Gradle can compile the Scala code. Gradle is going through all the JVM language code blocks, all the Groovy, all the Java, all the Scala, and compiling everything for us in one go. And now we can just run our Scala code by calling the run Scala task. So now it's going to run the Scala code. And so I'll make this bigger. Here we can see hello concurrent world. So when it gets a defined message, it prints out hello concurrent world, and when it receives an undefined message, it is printing out correct. So our code is syntactically correct, and it worked as expected. And Gradle, which is written in the Groovy programming language, is really showing its utility. Here we have Java, which is a really good language, which has underpinned the modern internet and the embedded Internet of Things in so many ways. Then we have something like Groovy, which has contributed to the web application world through Grails, and has also now given us this wonderful build tool known as Gradle. And then we have the language we are learning now, Scala, which is a very powerful and useful object functional language. Let's just point out some of the important things in this Scala code. So first, because of Scala's functional expression in its language, we can strip out so much of the craft. So this is one of the first things that really strikes you if you're coming from the Java world when you're looking at Scala, is how you can do so much with such little code. For example, this case statement, Scala hasn't bothered implementing the switch construct. Instead, it focused on pattern matching, so we'll look at pattern matching code blocks in later topics. Now, val evaluates as a read-only variable. It's like a static final or a constant variable, where def, which we use for function evaluation, evaluates on every call. So it's the compiler knows to reevaluate the expression that's typed as def at every time that code is used, where when we have val, the compiler only needs to evaluate it once as a constant. The case underscore expression here acts like a Java switch statement default case. For the expression, the underscore is a placeholder, and it's like a placeholder wildcard. It can bind to many different types of variables. So acting as a default, it's able to act on all the messages that don't have a specific case. This simple example demonstrates the recipe for concurrent programming with functional languages. Now, firstly, this is all about maintaining state. A message allows an actor to change its state in a controlled and predictable way. based on the content of the message. So that change in state is always going to be thread safe. Then we need to be working with immutable objects, and strings are immutable. They can't be changed. The state is preserved through the immutable aspect of string. These strings that we are defining here to use as messages are immutable objects. They can't be changed. Their effect on the state is totally predictable and guaranteed. Message passing is asynchronous. The actor who sent the message can continue on while the receiving actor who received the message processes the message. Message passing is non-blocking. The actor who sent the message will not be blocked until the message has been processed by the receiver. So it's asynchronous and non-blocking. And also we have an operator for where we send the message. So this is fire and forget operation. So it doesn't have a callback. You just send the message and you're done. And so the Akka system has very successfully implemented this recipe for concurrent programming with functional languages. Now the Akka system and this actor system more generally has led to many success stories in the application development world. Now where are the common instances where you will need to have massively parallel systems? Well, there are two candidates. The first is websites. When you have millions of users hitting a website, you need to spin up many concurrent instances to deal with the demand of all the users. And so there is a framework known as the Play framework, which is implemented with Scala and the Akka system that's met that challenge very effectively. The second place is big data and processing and running algorithms. So there's an application framework written in Scala with Akka known as Apache Spark, which is one of the better real-time processing analytical machine learning frameworks. Welcome to the Eduonics Introduction to Scala course. This is Section 1, Functional Programming. What is it? Why can't I just use Java? In the last topic, we were talking about the functional model of JVM languages and how Scala was different to a pure functional model as we would find in Clojure, and how this created issues as the objects can change state, and in functional code the only thing that changes the state is the function. So Clojure is a true example of a functional programming language. In Clojure, after the function has finished, the existing type, the state of that type has not changed. The overall state of the code may have changed via the action of the function on the existing types, but the original types, their state has not changed. Whereas Groovy and Scala, because they are object-oriented language, the state of the object may change independent of the action of the function. So to address this, we have this idea of an immutable object. And so when we do functional code in Scala in particular, we have this emphasis on creating immutable objects. So let's have a look at the classic Scala immutable object now. Now, the Scala case class is an example of a type which is immutable. Now, here we have the constructor where we need to define the types of the input variables that we use when we create an instance of user. So here I am creating an instance of user. I'm calling it new user and I'm passing in a first name and a last name. Now I can always extract the username from my new user object via this syntax, but once I've created new user, I cannot change the name. So I can get the name, but I can't set the name. So if you are familiar with Java beans, a case class is like a bean that cannot change. It's a bean with getters and no setters. This is what we mean by an immutable object. So if our Scala functions act on these immutable objects, then the state of the code will not change as a result of any action on the object because it cannot change, it's immutable. So the functional model, the object functional model employed by Scala to achieve the true objectives of functional program relies on this idea of the immutable object. It's a reasonable question to ask, why is there so much emphasis on functional programming? Why is it important? Why can't I just use an object-oriented language like Java, because it does so many things for me and I understand it well? The answer comes in many ways because of changes in technology. There's a famous law known as Moore's law that says the central processing unit's clock speed increases linearly with time. Now, Moore's law has held really well for over 30 years. It's been a very strong and empirical law for all that time, but now it's starting to break down. And here we have graphical representation of Moore's law since 1970, and they're projecting it out to 2018. And we could see this increase in CPU clock speed has been very close to this line, but now it's starting to move away. It's starting to diverge to a logarithmic type of curve, as we can see here. It's starting to flatten out. But manufacturing costs are still continuing to decline, so it's always costing less to make CPUs. So what CPU manufacturers are now managing to do is increase the numbers of central processing units per chip. So now we have multi-core CPUs, and this means that we could start to write parallel or concurrent code. So if we want to write applications that are fully utilizing the technology they are running on, we can only speed up or increase the capacity of the application by creating processes that run in parallel. So that's what we're going to talk about now, and this is what functional program excels in, because it's easier to maintain the state of many processes running at the same time, or many concurrent processes. We can maintain and understand the state overall of the application when we use functional programming, because it has this strong emphasis on managing state. So that's why functional programming is becoming so important, because we can write better parallel or concurrent code. Now, the terminology for writing parallel code can be confusing in itself, so let's just quickly go through the definitions. So concurrency refers to managing more than one task at the same time. So when I have different tasks running at the same time, I need to manage the state of the variables that are involved in those tasks. Now, parallelism refers to executing more than one task at the same time. So when I'm talking about the parallel aspects of the code, I'm talking about the code when it's executing. When I'm talking about the concurrent aspects of the code, I'm talking more of managing the code. When I use the term concurrent parallel execution, what I'm talking to is parallel tasks running at the same time that are managed, and there are various models for that. Distributed computing is a special version of parallel computing where the processes that are running in parallel are running on different computers or nodes in a network. Now, Java is an object-oriented language, and its concurrency model is based on threads, where a thread can run a task, and threads share resources, and they are what's known as locking or blocking. When one variable is on a thread and it needs to be changed by some other thread, then locks are put on the variable, and a block to any change by other threads on the variable exists while the lock exists. Java has this executor framework, which is the managing part of the parallel execution, or the concurrent part. Then when we look at Clojure, which is a pure functional language, we see a much more sophisticated model. It's based on futures, delays, and promises. And the key thing that it gives you over Java is non-blocking. So it doesn't use locks. It's asynchronous. Futures define a task and place it on a thread without requiring the result immediately. It's asynchronous. Now, Scala has a different concurrency model to a pure functional language like Clojure. But Scala is functional, it's fully functional, but it has a special reactive model for concurrency, and this is a big part of Scala's success, is Scala's concurrency, or Scala's way of managing parallel processes, is very effective and scales to thousands of nodes. The Scala concurrency model, the worker threads share no state with other threads, but it's a share-nothing, non-blocking parallel management or concurrency system. Now in Scala we call the worker or the worker thread an actor, and it sends asynchronous messages to other worker threads, and they are processed asynchronously or non-blocking. Now Clojure and Scala share this idea of software transactional memory, and this is similar to a database transactional management system where you have some sort of transactional process that ensures the integrity of the state of the variables. So you have this ability to roll back a transaction. If a transaction is considered illegal or corrupt, then you can roll it back to the previous state. So we've talked about the need for functional program, why it's useful, why it's important to learn it now. And Java is not a functional language, but Scala is. And in fact, Java is an imperative language that's based on a sequence of statements. Now, pure functional code is what we call declarative programming, where we define the rules. For a pure function, the inputs will always map to the same outputs, and there will be no change in state. It's self-contained and stateless, so it's perfect for concurrent programming. Whereas in imperative code like Java, we must work much harder to maintain the state. So now we've established the case for using Scala and evolving beyond Java, let's just quickly review function syntax in Scala. Here in my Scala runner object, analogous to a Java main class, I create an instance of this Scala class type. And in this Scala class, I have defined a function with the keyword I use for defining functions, def. We've talked about the syntax of its handle, its input parameters, and its output type, and its behavior. So now if I create an instance of this class, I can call the function simply by passing in the input parameters, and it will go into the class and return a result. Now I can extend this behavior by extending my Scala class. So here I have a class which is like a simple factory, and it has a constructor. This is a class constructor where I define my input variables. Now we don't have the sort of constructor block that we have in Java. In Scala, when our input parameters come into our code, we can just use them as though it was a constructor. I can overload constructors with this syntax. So in the case where only the X input is supplied, then this syntax here redirects the X to be combined with the 1 in this expression. So I can handle 1 or 2 inputs with some predefined behavior using the this keyword. And notice I am using the def, which I use for functions. So this is an example of the functional flavor of Scala. So I don't have a constructor. In the case both parameters are supplied, result is evaluated as a static final variable. In the case where only X is supplied, then this function passes through with the value 1 for Y to the result variable. And then I can access result in a factory method supplied product where I'm defining my output. So we can see from these two examples, here we have a very simple class and we have a simple function defined, and by using the Scala behavior with its constructor and the overloaded constructor syntax, we can create a function with more complex behavior using minimal lines of code. And this is the key thing, is we are, by the functional aspects of Scala, starting to build up complex behavior with a minimal amount of code. And that's one of the reasons why Scala is such a popular language, as we will see in the final topic when we look at Scala success stories, and in particular the Play framework. In this project we have Java, Groovy and Scala all set up in the same application, and this is made possible by this build tool known as Gradle, which is written in Groovy. Now we will just demonstrate how we can build and run the Scala code with the Java code. So if we go down here and I use the compile Scala task, so we run the compile Scala task, so you can see it's compiled the Java. So the Scala code fully compatible with Java. So it compiled the Java and it compiled the Scala. So now what we'll do is we will run this Scala version of a main class because it has a main method. We'll check that the syntax for these function calls and the associated classes is correct. So if we do the run Scala task, we can see we have this output, Scala simple function 6. So this is the output for this line here. We used an instance of our Scala class to call its function multiply, passing in the input parameters that it defined and expected, and its behavior returned the correct value 6. Then we used an instance of our Scala product factory, which is a little bit more complicated because we have two constructors. One is an overloaded constructor. So the first time we called it with its full parameters that it expected, so we called its full constructor, and so it went through and evaluated the static final variable result and correctly returned result. So 3 times 4 is 12. So we followed the correct and expected flow there. Then we called it with its overloaded constructor and we saw its functional behavior. So it's got an overloaded constructor defined like a function that handles the case of just an x input variable. So we saw the functional flavor and we see that that syntax is correctly working because 1 times 3 is 3. And we also saw how we can run Scala inside the Java virtual machine alongside Java and Groovy code. Welcome to the Eduonix Introduction to Scala course. This is the final topic in section 1, Scala success stories, Akka, Spark and the Play framework. In this topic we're going to write some demonstration code in Scala to use inside the frameworks Apache Spark and Play. We're going to show how, by using Scala as their core programming language, these frameworks were able to be successful. Both these frameworks, Spark and Play, need to be able to run in a massively parallel environment, and they were able to achieve that by implementing Spark's concurrency framework, Akka, and this is the link to Akka. And we can see at the Akka link in the Akka documentation how these applications Play and Spark were able to be successful because of the high performance in concurrency that can be achieved with the Akka architecture. So on a single machine they can run up to 50 million messages a second, and for each actor, if they have 2.5 million actors, they can fit them in a gigabyte of memory. So by being able to run such massively parallel applications with such small resource requirements, this was the key attribute that allowed Spark and Play to stand out and differentiate themselves and become successful frameworks. So Akka was written in Scala, and as of the later Scala 2.10 and beyond, Akka has been merged into the Scala source. Now, as we looked at before in the simple code example where we created an actor system, the actor model has actors that respond to immutable messages in a non-blocking asynchronous way. And you can see from that website, this is a very effective and powerful system. Now, Play uses Akka. This is the link for Play. This is the link for Play, and here we can download the Play binaries to create Play applications, and we can find the documentation here. You can see it's advertising itself as a web framework for Java and Scala. You saw in our previous code examples that we can easily run Java, Scala and Groovy all together in one application. Now Play is written in Scala, so it has a Java API which has led to its increasing adoption by Java users. But when we write with the native Scala code, we end up with much cleaner and less verbose code. Using Scala, we will follow this play documentation and create a simple to-do list web application. And we can use that as a way to show that you don't need to be expert in Scala to get really good results using Scala. Here we have an implementation of the play documentation. So here we have the documentation link, and it goes through the steps to set up this Scala to-do application. And so we've implemented all the steps a little bit different, because one of the things you'll find with Scala is that different Scala libraries work in slightly different ways. So this code needs to actually be modified to run in the latest Scala, which is what we have done here. Now, firstly, it follows the Model View Controller Framework, or MVC. So we have a controller package, a model package, and some views. So we will start with our controller. So this is our entry point for the application, and it's using our object. So it's defining a static block of code that can run like a main class. So we don't have a main method here, but we're extending controller, and that's where the entry point code is established. And straight away we could see the functional nature of the code, which is the key learning goal. So one of the things about the functional code and functions is that we bind immutable objects with functions. So here we have an immutable object. It's a string, and we're using a function to put the value of the string into a model text. So this non-empty text will display in one of the views. So we're using a function, in this case a lambda expression, to bind it to a field. So this is the functional flavor. If we were to write this in Java, some other language, it would be more verbose. Now, this action type implements an interface, so it can be implemented in different ways. So here it's passing a value to its constructor, and here it's passing a different value to its constructor. So it's implemented in different ways with different constructors. Here we are defining a function, new task, and we are using this idea of an implicit variable. We can mark a parameter in the constructor for action as implicit. Now once again we're coming down to this functional idea of binding immutable objects with functions. And so this implicit sets up a special type of function binding. So what will happen here is, because we've marked this as implicit, if the compiler can't find a type to pass in that it's happy with, then anywhere in the scope where it can find the type that makes sense, it's going to use that type. So it's a more powerful binding. Here we are using a lambda expression. So we have one variable here and a lambda expression that binds it to this view object. And so the lambda expression just does the binding. But here things are a bit more complicated. In a web application, we can have different types of requests from the client. So by marking this parameter as implicit, we are saying to the function, try as hard as you can to bind this to the correct variable that's in scope. So here we are creating two what we call CRUD methods that work with tasks types. So we're creating a new task and we're deleting a task. So what we'll do now is we'll look at our task code. So this is a file, task.scala, where we have a task which is a static object, and we have a case class that is task. Now we understand from our previous work that a case class is an immutable object, and we can set its ID and its description. Now this code can be best understood if we understand that this syntax here is working with this package. So this is an SQL parser, and this task is implementing an SQL parser where it will work on an SQL result set. So when we perform a query like this, we can call that query using the functional SQL code in this package, and we can bind the results of the SQL query, which is a result set, to this task object. And this task object is set up with these methods, which, as long as there's an ID and a label with these types, it can map them to this task immutable object. So the data from this query is bound to this task parser type, which then has functions that bind to these fields and then map them to an immutable case class instance of task. So this gives you an introduction of how this Scala model persistence code is working with the classes and the functions in this package to bind data from result sets to immutable case class objects, and then we can create and delete and perform persistence level operations. Now the next operation that we do is we need to, once we are responding to web requests with our model and our persistence layer, is have the response flow, so we are sending out the results of those requests to the correct views via our pre-configured routes. View type here, which is a HTML page. So there is some model binding going on here where we are binding our task model with this syntax in a HTML view. This is getting a long way from pure Scala, so we won't worry so much, other than to say that our Scala types using this @ syntax can be bound to HTML widgets. The easiest way to build and run our Play Framework Scala application is using the Scala build tool, which we can download and configure from here, the SBT configuration files. So there are two, one top level one called build SBT and another one which configures the plugins. Now for build SBT, we just set up the dependencies, and here we can see we have a JDBC dependency. We have this ANORM, which provides all that SQL parser and persistence layer code. And then for our plugins, we use a Gradle-like syntax here to declare our versions and our repositories for our dependencies. So what we'll do now is we'll just quickly build and run this code with SBT. To build the code in a terminal, in the same directory that contains the top level build SBT file, if I simply type SBT clean compile, it will build the code. So now I'm running this command, SBT clean compile, and the first time you build it, it needs to download a lot of dependencies. So it can take a while, especially if you don't have a fast internet connection. But then once you've downloaded all the dependencies, the next time you build it, it doesn't take so long. So it built fairly quickly for me, as you can see, but for you, the first time, it will take longer. So now if I simply type SBT run, it will run the web application in an embedded Jetty server. So you can see it's running the application. So now in a browser, if I go to localhost 9000, I will see the application. So I open up a browser, I'll bring this down so you can see the URL, and I type localhost. And it will run the simple to-do application. Now, the first time it's asking you that you need to run this SQL script. That's from the ANORM SQL dependency. So I apply the script and it creates the embedded database. So that's just a security check. So this is the label that we bound to the field type. So if we go to the code and we go to the application, you can see this is the label getting bound to the view widget. So this is quite a functional little application for not much code. So if we write a task and we create it, you can see we're creating a task and we can delete that task. The application is quite functional and it's working okay. So these are not exceptions, these are just messages. So the application is working. So I hope you can see that Scala, it's functional code which can take a while to get a handle on, but it leads to very clean, very simple code that does a lot with not many lines, so it's very maintainable. So the next Scala framework we will look at is Apache Spark, and this is the website for Apache Spark. If you go to this website, you can find links to the documentation and where you can download the binaries, and it describes what Spark is. So Spark is an algorithm machine for working with big data that's capable of scaling to thousands of concurrent parallel processes, and it does that much faster than anything else. And that speed and that ability to scale up to such large amounts of parallel processes comes because it's using Akka. So it all comes down to Akka and that Akka architecture framework and the whole functional recipe of using these binding functions with immutable objects. And we just saw how we could make quite a functional little web application using the Play framework and Scala and the functional binding. In the next video, we will create some Scala code to drive some Spark analytical processes. Welcome to the Eduonics Introduction to Scala Section 1. This is the second video in the final topic for Section 1, Scala Success Stories, Akka, Spark and the Play framework. In the previous video, we created some Scala code to construct a simple Play framework application. In this video, we will create some Scala code to drive some Spark analytical processes. This is the application where I will construct my Spark Scala code. This is a multi-module Gradle application. This is the top level Gradle build file where I declare a Spark version and a Hadoop version because Spark is integrated with the Hadoop Big Data framework. Here I set up my modules, so I have a Java module and a Scala module. If I go into my Scala module, build Gradle, I can see where I declare my Spark dependencies for my Spark code, and I'm using Gradle's Scala plugin. So this is a quick overview of how I configure Gradle as a build tool to work with Scala and Spark for this code. Now this code is very simple, just to illustrate the style of a Scala code, and the basic pattern that we will follow over and over again is working with immutable objects and functions. So I have this object which is acting like a Java main class called basic stats runner, and it's defining a main method, so it's the entry point for my code. And then I have a class where I'm defining a function, and now I'm using my function syntax with very high level types. So I'm using a Java URL as a return type, and then I'm calling the class type to find a resource as a stream on the file system. I have an import here where I am importing the Spark configuration type and the Spark context type. I use a Spark configuration to create a Spark context. Now in my main method, I start off by creating a static final configuration object where I give a name to the code, and I also set what's known as a Spark master URL. So Spark has various modes depending on how you run it. It has a local mode where you can run it locally on your own machine for development and testing. It has a yarn mode where you run it with the cluster manager yarn, and it has a standalone mode, and that's when it runs on a cluster but it runs under its own management system. Here we're setting it to be local mode, and this wildcard tells Spark to discover how many cores are available, and then it sets an appropriate number of threads based on the number of cores that are available. Once we have this static final conf object, then we create a context, SC, and our SC context, our Spark context, is our hook into the system. Now we are going to create a basic stats type. So we create a class, basic stats, and the constructor that we give it is a file name on the system where we have some data. The data is a CSV list of thousands of banks from New York. So it's just a good commercial data set to develop code on. Here we can see the location of the file in the system in relationship to the Spark code, which is in the Scala directory. This is where the Spark packages begin. And then at the same level, we have another directory called resources where we have our data file. So we just pass in the name of the data file to our Spark class. And then we call for the URL from our function getDataFile that obtains the URL for the location of the file. And so it's using the Java code getClass getResource, so this is the same Java syntax, that will use the class path to find the file. So we get the URL for the file, and with the URL we can use the Spark context to obtain an in-memory representation of the data as what's known as a resilient distributed data set, or Spark's RDD. The RDD is the fundamental data structure for Spark, and it's firmly in our recipe of functions acting on immutable objects. An RDD is immutable, and it's protected as well. In a sense, you can't easily create them. You get them from operations with the Spark context on data. So here we are using the URL from our function we defined in the basic stats class, getDataFile. This URL points to a file on the file system, and then our Spark context that we created pulls in the data into memory as an in-memory RDD, and this RDD is immutable. And any actions that we perform with functions on the RDD do not change this RDD. We can't change it. But if we act on it with a function, we can produce a new RDD from the function that has a new representation or new types of data within it. So this is the key architecture that we see with functional programming, concurrent programming, and Scala, that we have immutable objects that are acted on by functions. The objects are immutable, they do not change, but the process of acting on that object can produce new objects, but the original objects are immutable. And with this pattern and with the Akka actor system, we can then scale up to thousands of parallel processes that we can manage successfully. Without that pattern, we would not be able to do it as effectively and efficiently. And for the scale that these programs like the Play Framework and Spark scale up to, I doubt if we would be able to do it at all without that functional programming pattern. An immutable object, a function produces a new object. The objects do not change. And when we are managing our parallel processes with our concurrency, we are using an asynchronous non-blocking system. So what we'll do now is we will run this code with Gradle, and we'll see if we can perform a very simple basic stats operation where we can do a count on the data. So our RDD type has a number of functions built into it that we can call, so we can call the count function. Now we can use Groovy via Gradle to compile and run our Scala application. So first we choose the compile Scala task, and that will compile our code. I'll just make this bigger so we can see the output. So the Java code is compiled and up to date. Now it's compiling the Scala code. And that worked out, it compiled okay. So the Scala compilation via Groovy and Gradle completed successfully. So now we will run our Scala application. So we run our Scala application, and you can see Spark is outputting a lot of data, and it built and ran successfully, and this is our output. we found that in our test data set we had 10,001 lines. So we have the commercial data for 10,001 banks in this data file. So we were able to successfully run a simple Scala Apache Spark application. In the next section, we will go through in more detail how we set up our Gradle Scala applications and our SBT applications, and we'll also look at an Eclipse Scala plugin. So we will look at how we can create Scala applications with build tools like Gradle or Eclipse. Welcome to the Eduonics Introduction to Scala course. This is section 2, set up a Scala development environment with the simple build tool. In this section, we will cover setting up a Scala development environment. Now it's easy enough to set up a console with Scala, but to use Scala for professional work, you need to work with the tools of software engineering, and in particular, what software engineers call build tools. We are starting this section with the build tool that's developed exclusively for Scala, known as the Simple Build Tool, or SBT. Our learning objectives for this unit are 1. How to install, then the syntax to use SBT to configure projects and project conventions. Then we will look at the configuration file to build the application with SBT. This file is known as build.sbt. We will learn its syntax. Then we will learn about the many SBT plugins, how you use them. We will go for an example to create what is known as a runtime jar that contains all the dependencies for our application as well as our application source code. Then we will look at how you can resolve transitive dependency issues using remote and local repositories. Now, SBT has a steep learning curve. It's not really simple, and it's best suited for pure Scala projects and is by far the best build tool when we work with the Play framework. It also works well with IntelliJ Community Edition. This is the website where we can download SBT. So here is the website. It has the download link as the very first thing you see. Now, we're only supporting Ubuntu 14.04. Now, it's possible to easily install it on Windows and other platforms. The best download is the zip. So if we download the zip, I've previously downloaded it, but this is the best one to choose. Once you download the zip file, you unpack it into a directory in your home directory and rename it to something that's easy to put on the system path. I've chosen SBT. If we look inside this directory, we have a bin directory, and here we have an SBT launch jar and some scripts. Then we also have a configuration directory, but for now we don't need to worry about that. In fact, we're not going to work with anything inside this directory at all. All we're going to do is put this jar on the system path by putting this directory bin on the system path. We do that very simply by going to the home directory in the text editor and opening up our .bashrc file. So here you can see I have done that by setting path to be whatever path was before, and then appending onto my old path the file path to that bin directory. So here we can see that syntax a bit bigger. So the final path export statement, whatever I'd set up on my path previously, and then the path to the bin directory that contains the SBT launch jar. Now I could have some other things on my path, for instance Java home. So here I am appending Java home to the path, but my final export statement contains that path to the bin directory that contains the SBT launch jar. Now if I type source.bashrc in my home directory in a terminal, that will reset all my path variables and it will put SBT on the path. So now if I just type SBT -H, I should have SBT, and there it is. We can see we have the help for SBT. So now I'm ready to move on and create a project using SBT. And to do that, I must create an empty directory where I want to configure my project template. To create a project template with the default folders that I need for an SBT project, I'm going to use two SBT commands, the SBT set command and the SBT session command. So I make an empty directory, I change into that directory, and then I issue these set commands. And this is pure Scala syntax. What I'm doing here is working in a Scala build environment. So let's make an empty directory, call it project_SBT, and now I'll change into that directory. And now I issue the SBT command, and SBT will come up, and then I will use my Scala versions. Now what I will do is initially set my Scala version to be 2.11.5. So we'll start off with the latest version of Scala. So in our terminal, in the directory, we now issue this command, and you can see it's setting up so it will have that version of Scala. Now we're going to go copy the rest of the commands, so the name and the version, and this image here in the documentation shows you what you should have when everything works out. Now nothing's been set up in the project yet until we save our SBT session, and this will create our SBT configuration file build.sbt for us with the correct syntax. Now there are many more options for set, but this is sufficient for now. If we go to our project _SBT, here it is, if we look in there now, we have a build SBT file, we have this project directory, and we have a target directory. And so these are various build directories for the various aspects of our projects and their dependencies. If we open up our SBT file, we can see it simply has the commands that we issued. Now just with these simple steps, we're in a position to immediately create Scala code. We can demonstrate that by creating a Scala file now. So in a text editor, we create a new document, call it Scala template, and in this document we can paste this code, which is a very simple Scala object. So we paste this very simple code. Notice we don't have a package here. We haven't defined any Scala packages. So we save this. So now in a terminal, if we type SBT compile, it will build the code in the file Scala template. So now we can run that with just SBT run. It should print out, and you can see it printed out hello project world. So we're in a position immediately with SBT to be productive, but we need to do a lot more work than this. What we need to do is follow the convention for Scala code. So SBT does not impose any conventions upon us, but we need to follow those conventions, because if we are using other dependencies, libraries, and what are known as SBT plugins, often they will expect a certain directory layout. So we'll just quickly set up that directory layout now. To follow the convention for Scala projects, I first create a source directory, then a main directory, then I create a resources directory and a Scala directory. And my Scala directory is the top level source directory. Below the Scala directory, I create the directories for the packages. So I have a COM package, an Eduonic package, and now I put my Scala template file inside the Eduonics package. So now I have my Scala template file inside the Eduonics package. If I open that file up, I can see now I give it the package declaration because it's in that package. And now I'm importing this library from a package known as the string metric library. This is a very useful library written in Scala for all sorts of algorithmic work. And so this is the import, and I'm using my underscore as a wildcard. And here I'm actually using a Scala class from the library to do a comparison on two strings. And then according to a particular metric, it's going to evaluate the similarity of those two strings, and then using Scala's print functions, and we can see more about how to print different types of strings to the console, I'm going to print out the result of this string metric calculation. We've got still a simple Scala project, but it's showing how you can use sophisticated dependencies. And now what we're going to do is look at how can we set up our Scala simple build tool configuration file, build.sbt, so it will pull in this dependency so we can use it in our Scala code. This is the website for the Scala string metric library. If we go to this website, you can see the source code which is written in Scala for the library, which I encourage you to read and explore because it's very accessible and very good. If we scroll down, he has provided for you how to set up the dependencies for different Scala build environments. So here we can see if we are building Scala with Maven or Gradle, and SBT, which is what we are using here. This is one example of how we can include the dependency. If we go to our Scala build file, we can add the dependencies in a slightly different way, because if we want more than one dependency, this is the syntax for when we use more than one dependency. So we've added the dependency. So we've removed our previous version of Scala template.scala, and we've moved it into the correct package folder, but it still has the same name. So to make sure we compile the latest version of the code, first we must issue sbt clean. So we clean any compilation that occurred previously. Now we run sbt compile, and we can be sure we are running on the latest source. Now it could well compile at this time, and it compiled, and now we can run. And it may well run because we only have one dependency, and we could have some errors here. This time it worked. If we review our build.sbt file, which configures our simple build tool SBT for this project, you can see our Scala version is 2.11.5, or a later Scala version. But if we go to the website for Rocky Madden and we copy the version that he recommends and we compare it to our simple build tool version, if we paste 27.4, so we use the one recommended by Rocky Madden, first we clean, then we compile, and we have these errors. Key point we're trying to get across here is that you can often have dependency clashes, or what's known as transitive dependency clashes, when you are using the latest Scala versions with older but useful Scala libraries. So we've looked at our SBT syntax for adding dependencies, and we've looked at how we can use project conventions with our package layout source main Scala. And we've looked at the syntax for build SBT. What we'll do now is we'll look at SBT plugins, and we'll use a plugin to create what's known as a runtime jar. The plugin we will use is called SBT1jar, and here's its source code website on GitHub. If we go there, it has instructions for how to use it. So we need to create this plugins.sbt configuration file and add this line. If we look in our source code project, we go inside project here and we create our plugins SBT, and we add that line from the website. Now we have our plugins SBT where we've added the add SBT plugin line from the GitHub website for the 1jar plugin, and we must do some more work in our build.sbt. Now, to understand where this came from, he has on his GitHub website configuration examples. So we must set up some settings for our plugin. So if we look at the light configuration, here we have the import, we have the 1jar settings, and we declare a dependency that this plugin needs. Now we have this dependency here, and we have the string metric dependency. These dependencies have to come from these things known as repositories on the internet, and this is how we set up repositories in SBT. So we have the name of the repository and the link to where the repository exists on the internet. So now we clean and compile, and we can chain our commands as long as we don't have a mistake in the syntax. So we clean first, then we compile, and you can see now it's resolving all the dependencies that the plugin needs. So now we have compiled the source code with the Scala compiler. We can now create our executable jar with our SBT1jar plugin, and we just issue that command SBT1jar. So we run this, and it will get all the source code and all the dependencies and package it all into one jar, which we can run, and when our application source code runs, it will find its dependencies in the jar on the class path. If we look inside the target directory, we look inside the Scala directory, we can see we have the one jar, and this has the dependencies. If we cut this jar from here and move it to the top level directory, and then we rename this jar to something friendly, let's call it Scala 1 jar, and now we can run this with Java jar because it's executable. Let's run the jar, see if everything worked out, and you can see it ran the dependency library and our application source code all from one runtime jar. So this is a way we can package and deploy our Scala applications using the SBT plugin OneJar. Welcome to the Eduonics Introduction to Scala course. This is Section 2, Topic Scala IDE, Scala Worksheet and SBT Console REPL. In this topic, we're going to look at some alternatives for setting up a Scala development environment. We're going to first look at what's known as the Scala IDE. That's an integrated development environment specifically for Scala, and it's a version of Eclipse configured for Scala. Then we're going to use the Scala IDE to create what's known as a Scala worksheet and compare that to what's known as the Scala REPL. Now here we have a link to the Scala REPL. If we go to that link, we can read about what's known as the Scala REPL, which stands for Read, Evaluate and Print Loop. It's a quick way to run fragments of Scala or Scala scripts, if you like, and look at the results. And in particular, you can discover the types or the outputs of different complex functions. So it's a good tool. Now, the reason we are looking at how we can set up the Scala REPL using the SBT console, we can quickly swap between different Scala versions. So if we install a Scala library and use the Scala REPL from the Scala library, we are locked into that Scala version. But if we use the SBT console for our REPL, we can quickly change between Scala versions for our REPL. In the first instance, you can think of Scala worksheets as an alternative to the functionality found in the Scala REPL, but really, while they are similar, you would use them for different things, and we will work through examples with the worksheet and the REPL and show how they are useful. Now, this is a link to the Scala worksheet configuration information. If we go to this link, you can see they are talking about installing this Scala IDE, which is just really a version of Eclipse set up for Scala. And you can use that for Scala development and creating standalone Scala projects, as well as integrating Scala worksheets. So we will start, firstly, install the Scala IDE, which is a version of Eclipse, create a new Scala project with the correct convention structure, source main Scala. Then in that project, we will create a Scala worksheet. And this is what they look like, and we will work through how you can use them in your application development in a useful way. And then we will create a simple application, and we will also see how the SBT console REPL can also help us work through the issues we encounter in Scala application development. This is the download link for the Scala IDE. It is possible to use an Eclipse update, install the Scala IDE as an Eclipse plugin, but we recommend using the pre-configured setup Scala IDE from this download link. If we go there, we simply need to choose the one for our operating system. You extract the download to a folder. By default, it will extract to a folder called Eclipse, but it's a good idea to rename it if you have other Eclipse installations. I have renamed mine to Scala Eclipse. Inside there, you simply click on the Eclipse icon, and this will start up the Scala IDE. Now when it starts up, it's defaulting to my home directory. If I go browse, I can create a new workspace directory. I've created a folder for worksheet project, and this will be my workspace when I use the Scala IDE. So now click OK. You can see that I have created this directory, which is now empty. And Scala Eclipse is booting up. Resize it so I can close the outline. And so this is my default perspective. And you can see I have my Scala options here. So it's all set up. Now I want to create a new project, so I go File, New, Scala Project, give it a name. I'm calling it Worksheet, Finish. It's configuring. setting up things. You can see it's starting to create it in the Package Explorer. If I open this up, I have a source directory, but I don't have the conventional Scala structure. So I'll exit out of this now and create my main Scala and resource packages. So I exit out of Scala Eclipse, and inside here, inside source, I'm going to create my packages as before. Now here, inside the source created by Eclipse, I create a main directory, then a resources and a Scala directory. This is the top level source directory for the packages com.eduonix, and now I have two files, and that's a Scala file because it has the extension .scala. Now I have another file which I'm calling Scratchpad, has the extension .sc, and my Scratchpad is my Scala worksheet. So .sc for Scala worksheet and .scala for Scala source. Now the Scratchpad worksheet is good for quickly trying out things. I can run it against the compiler quickly. I can then put it into my main source. So what I need to do now is restart Eclipse, get Eclipse to pick up my new directory structure and the source files that I've included. So as before, inside my Scala Eclipse directory, double click on the Eclipse icon, and the Scala Eclipse will boot up, checking I'm defaulting to the correct workspace. And when it boots up, I will see my project, but then I'm going to have to refresh my project for it to pick up the new structure that I created inside the project directory. So if we go here and we open this up, you can see it's not picking up my new files and folders. So if I hit the F5 key, it will refresh the project. You can see it's refreshing down there, and now it's picked up the new source and the new structure. Now I have created a resources directory. If I go to my workspace, I go to my project in my workspace, I go to source, main, and I look in resources. Here I have two files, and these files are those commercial bank files. So they're good examples of a sort of raw data you would work with in a Scala application that was working as a parser. That is, it reads raw data and structures it into being something more useful. So now in our main source package, we are seeing an incorrect structure. We have main Scala com eduonix. That's not what we want. We want our Scala package to be our top level source. This is important because we need to structure the class path. So we won't be able to easily find these resources in the resource directory because Eclipse is telling us our class path is broken. So the way we do that, the way we fix that is we right click on the project and we go to build path. Then we go to configure build path. Then we go to our source directory. We need to configure our source directory. Now we remove what we have now because it's broken. And now we add a folder. So we go inside source, we go in main, and we add resources and Scala. Okay. So now we've set up our Scala directory and our resources directory as top level source folders. So now if we look, we have the correct structure. Now we are using the convention so that when we call from Scala to find these raw data files, we will find them because we have our class path set up correctly. That's a key point. Now we can see the Scala IDE is nicely differentiating our Scala file and our Scala worksheet. Let's open up our Scala worksheet. This is our Scala worksheet. Here we have a test line. So this is just a string from the raw data. So if we open up the test, this is a smaller version of this file. This is what our data looks like if we open up one of the files. You see we have a schema, ID, name, billing. So if we count this, you will find there are 9. So if we were to grab any one string or any one line from this file, then it would look like this line here in our Scala worksheet. If we make some room for it there, you can see we have this line. Now we are splitting this line on a tab here, and we are then looking at the length of the split. Now the split is just an array. So this is a value, which is a test line, constant. Then we are just doing the typical string split, and then we are applying a function. Just look at this closely. We have our underscore, which we have already seen acts in many cases as a wildcard input. So this is an input or a dummy placeholder for each token in the split. And then this is our string trim function, which trims off any white space. So we end up with this valcol, which is just an array, and here we are testing for the length of the array. Now this is very useful because it's showing us information about our code in real time. For instance, it's telling us our variable test line is a string, and it's showing us what it's evaluating to as a string. Then it's telling us that our variable cols is an array of strings, and it's showing us what our string array looks like. So we have some issues here because we've got these two empty strings, and also it's telling us what our k is evaluating to, an int, and it's 10. Now this is also useful because we know in our schema we have 9 columns, but here we have 10 elements in our array. So this empty string is an error. Now the only way we would discover this if we didn't use the Scala worksheet in this project, if we have our Scala parser code, so we open our Scala parser code, we would need to run our Scala code, and then we would get index array exceptions or missing data. So the Scala Scratchpad, the Scala worksheet, is letting us see or test our Scala code, test our output, discover what are the issues at compile time, so we don't need to actually build and run the code, so we can create our application source code quicker when we use Scala worksheets. They're very useful. Let's look at how we can do the same thing now with the SBT console REPL. Because we have SBT on the path, if we type SBT console in a terminal, hit enter, the SBT console will boot up and we will have a REPL function in the terminal. So here we have, this is equivalent of the Scala REPL. If we installed the Scala libraries and set up Scala as native to the machine, we could just get the Scala REPL that way, but by using SBT and SBT console, we are not tied down to any one Scala version. If we copy our string from our Scala worksheet into the console, now what we need to do is go back and space it because in the copying it lost some spaces. So now we've correctly delimited it, the string with the correct number of spaces for a tab. We can count the tokens. We have 1, 2, 3, 4, 5, 6, 7, 8 tokens. So this is why our Scala worksheet was incorrect, because it's counting as 10 tokens. It's counting some empty tokens. So we found the Scala worksheet is not picking it up as well as we like. So we're looking at an alternative, which is the Scala REPL via the SBT console. So we hit enter, and you can see it's doing pretty much the same thing as what the Scala worksheet is doing. It's telling us it's a string. So now we can do the split. So if we put this value in, we are putting the values in. So now in the Scala REPL we have created our test line and our cols variable. So now we can look at the length of the split, and it's saying it's picking it up as 1, so it's not even getting the split correctly. So we could be having the problem with our tab delimitation. It's not picking these spaces up as tab. So we have an alternative syntax we can use, and we will split on 2 or more spaces. 1, 2 plus spaces, so we want at least 2 spaces, and more than 2 spaces. So here where we have Alliance Securities, Inc., we want all that to be 1 token, so we need more than 2 spaces, so 2 or more spaces. So that's the expression. So we hit that, and now we will look at this for cols 2, the length for cols 2, and you can see it's 8. So this was the actual correct expression. So we were able to use the Scala REPL via the SBT console to find the correct expression to split the string into the correct number of tokens for our tokenization. So whether we use the Scala REPL or the Scala worksheet, we use them to quickly test out and discover critical issues in the code, like what will be the eventual type returned from complex functions, and what will be the quirks, like in particular parsing expressions or regular expressions, so we can split strings. What will be the result? Will it work on our target strings? So these are classic examples of where the Scratchpad or the Scala REPL can speed up the development of your source code. So let's look at our source code now. So this is our parser. It's going to parse the input data. So we have a static object, a Scratchpad object, which has our main method. Then we create an instance of our Scala parser class, and we pass in the relative path to our raw data file. Then using the instance of a Scala parser class, we call its function parseLines, which is defined in this code block here. The constructor for the class, the input variable is defined here, and the constructor initialization code occurs here. We use the io.source class, which hooks into the Java NIO file package. Using the URL variable, we use that to create the path to the raw data. We use that access to the raw data, a buffered stream reader in Java, to get the lines, and then we act on the lines with our splitting function, and here we are just printing out a few of the structured tokens. So what we can do now is just run this. If we go run as a Scala application, and we can see the output here. Welcome to the EduOnix Introduction to Scala course. This is Section 2, Set up a Scala Development Environment with Gradle and IntelliJ Community Edition. In this video, we're going to learn how to set up IntelliJ Community Edition as a Scala integrated development environment using the Gradle build tool. This is the download link for IntelliJ, and if we go to that link, we see we can download the free Community Edition, which is an excellent IDE. So when we download this, we download it for the operating system of our choice. Here we will choose Linux. For the Linux system, we get an archive. We extract that archive with the Archive Manager to a directory which we rename as IDEA, so it's easy to use from the environment variables. In here we will have a bin directory. In the bin directory is a script called idea.sh, and the easiest way to get going with IntelliJ in most Linux environments is to create our own script which calls this script. This is the shell script that will start IntelliJ, and as you can see, it's just the full path to the location of the IntelliJ start script. So we save this in our home directory and we'll call it ij.sh. Now we can call our IntelliJ startup script with sh and the name of our script. So in the terminal, for the first time after we first installed IntelliJ, when we run this script, we will get a special boot up process. So we don't want to import anything. We accept the default value. We go to OK. And now the next steps are fairly crucial. Now you can choose whatever theme you like, but here what we're going to do, we will accept all the build tools, but we will turn off version control. We will look at the test tools and we will disable all, then just enable JUnit because we only want to use JUnit. We don't want swing, so we will turn swing off, disable swing. So we only want the build tools, the test tools. We can accept other tools, but we don't want plugin development. Now we go to next to featured plugin. Now here, this will download IntelliJ Scala library of choice, so we don't want to install the custom plugin here. So now we go start using IntelliJ, and by disabling all those functions, IntelliJ runs a lot faster and has a lot more memory available to the system because all those extra plugins use resources. So now we want to configure Gradle so that we can use Gradle with IntelliJ. Now we are ready to install Gradle. This is the Gradle download link. If we go there, we choose the binary only distribution. This will download a zip file of the latest Gradle, and we will extract that archive to a folder in our home directory called Gradle. Now here I've downloaded that binary zip, extracted it, and I've renamed the folder that I extracted to called Gradle. And in here I have a bin directory, and I need to put this bin directory on my system path to install Gradle. To put Gradle on the system path, I open the .bashrc in my home directory, and I create an environment variable called Gradle Home, and I give it the path to my top level folder that contains that bin directory. So if I look in the file system, here I have Gradle. This is the top level directory that contains the bin directory. So I give the path to that folder, not to the bin directory, but to the directory that contains the bin directory. And I have already previously set up Java Home, so you need to have Java Home, so that points to the top level directory that contains the bin directory for Java on your system, and I append these to my home, to my path variables. So here I have my path variable, and I append Gradle home, and I could also append Java home as well. So I will just extract this out. So here it is, we can see it a bit bigger. So Gradle home, export Gradle home, the directory that contains the bin directory. Then Java home to the directory that contains the bin directory. Then I put both these variables on my path with \bin for both variables. So now Java and Gradle are both on my system path. I save my \rc once I have put those variables in. And now in a terminal, in the home directory, if I type source.bashrc, so now I have Gradle in this terminal. Until I reboot the system, I will only have Gradle in the terminal where I have run.bashrc to reset the environment variables. So now I can check by typing Gradle -version, and if I run that command, if Gradle is set up correctly, it will look like this, and you can see it's found my Java home, and Gradle is now on the system path for this terminal. Until I reboot the machine, if I use another terminal and I want Gradle, I will have to issue source.bashrc to reset the environment variables. So now I will start IntelliJ in this terminal. So I'm starting IntelliJ in this terminal, so it will pick up Gradle home on the class path. It will pick up Gradle home on the system path. And now I'm going to go to Configure, Plugins, and check that the Gradle plugin is enabled. And I need to enable it because it wasn't there. So I go OK. And now I need to restart IntelliJ. And IntelliJ now will by default use the Gradle version that it picks up on the system path. So now what I'm going to do is create a new project. Now I'll just put this here where we can see it easily, and I select Gradle. Now I must select my project SDK. If necessary, I can go new and go to the directory that contains the bin directory. So I have my project SDK. Then I go next. I'll just make this so it fits into the view better. I choose next. Now I'm going to call this Scala Gradle, and the artifact ID can be Scala Gradle. Next. Now I'm going to choose local Gradle distribution, and it's picked up the location of Gradle from my Gradle home environment variable I created in the .bashrc file. I go next. Now the project location, I want to make it in a place where I can find it again. So I have a Scala Gradle directory here. I'll choose that. So now it's going to make it in a directory that I previously created, and I go finish. And now it's initialized. You can see down here, it's building here. It's configuring its Gradle artifacts, and once that finishes, that's finished, we'll be able to see what we have here. We have a build.gradle file, but there's no source directory, and we have a settings.gradle file. If we look in the settings.gradle file, it's simply the name of our project. It's possible to have multi-module projects in Gradle. Each module or project will have a name in the settings.gradle. Now if we go here to the File menu, go to Settings, and we choose Editor, we choose General, and we choose to select this box, change font size, zoom with Control mouse wheel. Select Apply, OK, and now if we use the mouse wheel and hold the Control key down, we can change the font size. Now this is not going to be a Java project, so we're going to change this to Scala. By changing this to Scala, we are now using the Scala plugin and telling Gradle that this is a Scala project. Now we have no source directory, we do not have the conventional project layout, main Scala, so now we can use our first Gradle task, and here it is. With this task we can now create the Scala convention for the layout of the directories and the class path. So now what we do is we go down to this little button here and we choose Gradle. We hit these two circle arrows. That refreshes the Gradle project and reconfigures all our tasks. So now it will pick up our new task. So if we go to Other, we can see here we now have our task create directories. So if we double click on create directories, and you can see it has now created a directory structure, and they're now set up as source directories. So in one task we were able to accomplish quite a lot. So this is why Gradle is a really good build tool, and in fact I recommend Gradle. So now we declare our dependencies, and the dependencies I've declared here are our string metric library we can use for algorithmic work, and our Scala library. And now I'm using an earlier version of Scala. I'm not using the latest version of Scala because in the next video we are going to create a microservice with Scala, and here is a dependency that I want to be safe, so I'm not using the latest Scala version. And so now what I need to do, that I have my dependencies, I also need to declare a place where I can obtain these dependencies from. These are my repositories, and in particular this dependency here, which is MQTT, a little message broker. This has a particular repository where we need to obtain it. These are my repositories. Gradle is able to work with many different types of repositories. So here we can see the type safe. They are a company that use Scala. So they have an Ivy repository, which is a good place to find Scala dependencies. Then we have two Maven repositories. Notice the syntax here. We can only have one repository per block. So we have two Maven repositories, so we need two Maven blocks to declare them. And this is the standard Maven central repositories. So that's my repositories. These are the locations for these dependencies. So now I need to create some new source. I've created my packages, com, eduonics, so I go new, and now I want to go file because I don't have any Scala attributes installed in IntelliJ. At the moment it's purely a Gradle project, and so Gradle knows about Scala, but IntelliJ doesn't know about Scala. So now I've made a Scala file. I've named it .scala. Now IntelliJ's picked it up now. So now it's say plugins supporting Scalas are found. Install the plugin, and we choose yes, because we don't want IntelliJ to choose the Scala libraries for us. We want to be able to choose the Scala libraries ourselves to match how we've configured Gradle. So now it's just installing the Scala plugin, but we'll be able to use our own Scala libraries when we do it this way. Now things get a little bit tricky here. So after the plugin installed, I was prompted to restart IntelliJ, which I did. Then I just copied the source code from our Eclipse worksheet project into my Scala file, scratchpad.scala. And once I pasted that in, I'm getting this message, no Scala SDK in module, set up Scala SDK. So I select that, and now it's saying use the library. So this is where I get the chance to choose what Scala library I want to use, because I don't want to use the latest Scala library. In fact, I want to use the Scala library that I declared in my Gradle project 10.6. So what I need to do now is go and download the correct Scala library that's compatible with the dependencies I'm using in this project. Now this is the download link for the Scala library jars. So I go to this download link and I find the version I want, 2.10.6. And now I can have it as a binary or as a typeset. What I want is to choose the binary option. So now I download those jars as an archive and I extract them to somewhere in my home directory. So I extracted the downloaded archive to this directory, Scala-2.10.6, and in here in the lib directory, these are all the jars that I need to get into the IntelliJ class path. So I go to create, then I choose browse, then I go to the directory where I extracted the archive that I downloaded, and I go to the lib directory, choose the lib directory, OK, and if it's happy look like this, then I choose OK, and now it's going to be busy here for a while as it reindexes all the code and sets up that library on the class path. So this can take a couple of minutes, particularly if you're on a less powerful machine. So we'll just pause. So after a few seconds after the reindexing finishes, you will see you now have all the code completion. So now Scala is available with full context support in the IDE. What this means is that you will be able to have code completion So if we look, for instance, at the source package, we can click on that. I can download or attach sources. So I have full support in the IDE, code completion, access to sources, and now I can build and run. So if I choose compile Scala, it will build the project. Compiles any Java code first. So this is building the project with Gradle. And now we can also run the code inside the IntelliJ IDE. So if we run Scratchpad, it's going to run that static object. That's the main method. Just let that go through. And we can see it ran as before. When we created the package structure, we also copied the files into resources that it needed. So it ran just as it ran in the Eclipse worksheet project. So these are all the steps that are required to set up a build environment with Gradle and Scala in IntelliJ, and this is my preferred way to work with Scala. Welcome to the Eduonics Introduction to Scala course. This is section 2, Scala Application Packaging. Create simple microservices with Scala. Now that we've completed all this work, setting up Scala development environments, what we'll do is we'll show how we can use the build tools that we've looked at to create useful application. And a type of application that's emerging that's very useful and very well suited to Scala code is what's known as a microservice. These are the learning objectives for this unit. 1. Understand what a microservice is. 2. Implement a microservice in Scala. And finally, demonstrate how useful the build tools are in application development and testing. To help understand what a microservice is, we can look at a traditional service. So here we have something, it's a bit more than a web page. It's a web application. It's got a traditional enterprise Java backend with a database. We've all worked on these sorts of applications in the past, possibly. Now, this is differentiated by microservices. When we look at the traditional service, it's monolithic and layered, and all the parts are strongly coupled. If you change one part, the other parts break. Whereas microservices are components of applications that we can put together in different configurations. They're all independent, they're loosely coupled. If we take one microservice out of the group, there's a good chance the rest of the microservices can be reconfigured to allow the application to continue. Now, microservices communicate remotely, often over the network. They need to support cheap, lightweight, remote communication, and that's what we're going to look at, how we can implement that in Scala. Now, we can use a protocol known as MQTT, and this is the website, the Wikipedia page for MQTT, which you can read, but basically I've summarized it here. MQTT is a machine-to-machine connectivity protocol. It's extremely lightweight, and it supports embedded and low-power processing devices. Basically what it's saying is it uses hardly any resources, and so we're putting it inside our application. We need this messaging service to have a very small footprint, and MQTT fits the bill. Now, when we use MQTT, we are using a protocol, so we need an implementation of that protocol. So we will implement two parts of the protocol in Scala, the publisher and the subscriber, but we need a third component known as a broker that acts as a glue that glues the messaging between the microservices. Now, a very small and efficient MQTT broker we can use for demonstration purposes is HiveMQ. If we go to this link in a browser, we find the website for HiveMQ. If we select HiveMQ, you can see you have a download link here. Give HiveMQ a try. When you download it, you'll have to sign up with your email, create an account, then you'll download an archive, which you then extract into a directory in your home directory. Now, when you extract that archive, you'll end up with this directory HiveMQ. And if we look in here, we can see we have a bin directory, and in here we have a HiveMQ jar. We have a bat file if we're running it on Windows, and we have a script if we are running it on Linux. Now what I need to do is make another directory, which I'm going to call HiveMQ. and I need to put this directory on the system path. So in my bashrc file, in my home directory, I create an environment variable, hivemq_home, and I give the path to that directory. Then I will go into my hivemq and copy the bin directory into the hivemq that's on the path. I create an empty data directory, and the log directory will be auto-generated when hivemq runs. Then I must give read-write permissions to this directory. Now, to implement microservices in Scala, first we will create a Scala Gradle project in IntelliJ just as previously. And in fact, you could use your previous project if you like, or you could make a new one. It's up to you. If you choose to refactor your existing Scala Gradle project or create a new one, you'll end up with something like this. So you'll have your Scala libraries installed and configured, and you'll have your build.gradle. So now you need to make a new top-level directory, hivemq, and in the hivemq top-level directory, you copy from the hivemq install bin directory the run.sh script. So that's where that run.sh script comes from. And now we also create our source directories with our build.gradle. So if we increase the font size here, we can see we have our task that creates our source directories. Here it is here that we ran previously. And we have our libraries and dependencies, so you can reuse most of this from your previous project or create it again. Now we have some tasks to run hivemq and to run a subscriber, run a publisher, and our fatjar task that is similar to the fatjar plugin in SBT. This is a fatjar task for Gradle, which will make the jars with all the dependencies they need for runtime. Then in our source, we will create the Scala source for our microservices, and we'll look at that now. So here we have our Scala file. In our Scala file, we have two static objects with main methods. We're calling one publisher, and we're calling the other subscriber. Now our subscriber object provides a service, so it's a microservice, and we're using the string metric Scala library to provide a string matching service. So when this object runs, it listens on this URL and it subscribes to this topic. So it receives messages, and these messages have this string, and when this object discovers this string, it knows it must respond, so it only reacts to messages that have this topic. Now this next block of code is part of the MQTT API. This becomes available in our code because we have this library in our dependencies, and this allows the client to connect to messages on this URL and port. Now we create an asynchronous callback handle by using this interface and creating an anonymous inner class where we override these messages that are in the interface MQTT callback. And the one we're interested in primarily is this message arrived. So the message that comes that matches the declared topic will arrive in this message arrived method as this message string. And here we can perform our metric calculations just as before and output the result. Just to summarize, our static subscriber object via its main method listens to a MQTT protocol service on this port and URL. It is bound to a topic. When it receives messages on this topic, it responds via its callback implementation in this message to perform a service operation on the message and output the result. Our object publisher does the inverse via its main method. It uses the MQTT API to connect to the MQTT broker hivemq on this topic and output this message to be string matched with the string metric library. It uses the same MQTT client API code, only this time it doesn't have that callback interface implementation. What it does, it just sends messages off to be matched. So it's asynchronous. It's send and forget. Once the message is sent, it continues on with what it needs to do. This is just simple Scala demonstration code using MQTT to show the idea of microservices, so they are little stateless, asynchronous, non-blocking services, very similar to the Akka asynchronous non-blocking process model that we looked at in the last section. One of our learning objectives is to demonstrate how useful build tools are in application development and testing. So we'll do that now. What we need to do is actually create runtime jars for both of our services. So we need to create a runtime jar for publisher, and we need to create a runtime jar for subscriber. Then we need to fire up our MQTT message broker, then run our subscriber, then run our publisher, and test that our results are working, test that our code is syntactically correct. Now, Gradle is a build tool where we can easily achieve tasks for all those processes. So here we have a task that will run HiveMQ. Here we have a task that will run our subscriber service, a task that will run our publisher service, and here we have a fat jar task that will make the runtime jar for subscriber and publisher. So now we will demonstrate how you can use these tasks. First, we must build the code. Now we have two objects, runtime objects, publisher and subscriber. So we define them as main class names, and we give the fully qualified name of the object. So we will build the publisher object first, so we comment out the class name for the subscriber. Then we find our clean task, we run our clean task. Then we run our build task. And because it's a Scala project, it knew to compile Scala, so now we've created our Scala code as bytecode for the Java virtual machine. Now we assemble all that bytecode with the fatjar task, so we run the fatjar task. Once that completes, we go in the project directory, we go in the build directory, we go in the libs directory, and we get the fatjar jar. So this is the one where it says all is the fat jar. We copy this into the top level folder of the project, and now we're going to rename it to pub, and we've renamed it to pub.jar. And now we repeat this process, comment out the publisher object, uncomment the subscriber object, run the clean task, run the build task, assemble the fat jar. Now we're going to go and find that jar and rename it to sub.jar. Now if we look in our tasks for run subscriber, it's going to look for subjar in the top level project directory, and run publisher will look for pubjar in the same place. And here we are declaring the fully qualified name of the main class objects for the Java virtual machine at runtime. So now we've used our fatjar task to assemble our runtime jars. We can use our run HiveMQ task to boot up the HiveMQ server, and we'll do that now. So now we find our run HiveMQ task in our Gradle menu, and we double click on that, and if everything's configured properly, HiveMQ will boot up. So here comes HiveMQ, and there appear to be no errors. Now we run the subscriber that will listen for those messages. So now we're running our subscriber task, and this will start up and will give us some messages when it is looking to connect. So it's connected to HiveMQ, so we've implemented the MQTT protocol successfully. So now we will run our publisher. Our publisher is running, and we will, as that boots up, we will change over to the subscriber terminal, because once the publisher boots up, it's going to send that message. So it sent the message, so I'll make this a bit bigger so you can see the match test for the similarity is this value of 0.33. So it's not very similar, but we have successfully run our microservice, and we've successfully connected the two microservices with the MQTT messaging protocol via HiveMQ, which we will just shut down now. Now, we will shut down all our services. Now, it's a good idea if you're running into problems when you're developing this sort of code to go to what's known as the systems monitor, which I'll just get it down here. And if you have any orphaned Java processes, they can hang on to resources. Now, here we can see these will stop future runs because they're going to hang on to directories and files. So we need to shut these down. So we go end process. So in this section, the focus has been on looking at what are the options for setting up a Scala development environment. And in this video in particular, our learning objectives were to look at what a microservice is, implement a very simple microservice in Scala, and show with its static objects its wide range of Java and Scala packages and libraries, its powerful object and functional syntax. The Scala is a great language for writing microservices, and I hope you could see how useful Gradle was as a build tool in building, packaging, deploying, and running associated services with our Scala code. Welcome to the Eduonics Introduction to Scala course. This is Section 3, Scala as a statically typed language. Let's focus in this video on understanding correctly what is meant by a statically typed language, but also what are types and what are systems of types. So there's our objectives. Now, a type system is a method for enforcing abstraction in programs. If you're coming from the Java world, you might be aware of generic types that allow this level of abstraction. Whereas a statically typed language just means the types are checked at compile time. If types are not well defined or types are used incorrectly, the compiler will throw an error and your program will not build. Now, types can be inferred by the compiler, and this means that we can have parameterization of types. So let's look at some example Scala code where we can see what a type system is, how we provide this abstraction with type systems, and what does it mean when we speak of parameterization and types together. We will use this Scala code to illustrate the following concepts. 1. Static typing. 2. Type systems. 3. Type parameterization, and how type systems and parameterization are used in the typical context of your everyday work as an application developer. Here we have a class called user entity. Now, we use entities when we are constructing what are known as object relational databases, or ORM. And here we are using a relational database package from Scala called Slick, and this is a very popular one that's emerging and starting to dominate the ORM space in the Scala world. Here is the website for Slick, and it comes from the premier Scala company, TypeSafe. And here they are flagging the fact when you create entities with their package that they are statically checked at compile time. When you work in a professional application, you can often have very large database with hundreds, if not thousands of entities. And so the relationship between those entities and their types becomes crucial, and often you don't discover errors until you run the code. And at runtime, type mismatches are discovered and the application fails, or worse, your data is incorrect. By this static compile time checking, you can create much more professional object relational mapping code. So in this code, when we are creating this Scala class user entity, we are using it as a table in a relational database. Now, when we have a class, we are defining a type. So a class is a way to define a type. Then we have these basic types like int and string. Everything, whether it's our own type we make or the pre-made types we use, they are all strong types. So the way these types are used is checked at compile time. For instance, in this projection function here, proven shape, we are declaring some types int string. When we use these variables, that we are defining as belonging to these types, we must use them as the type is intended. So we can't multiply a string, but we can multiply an integer. So the compiler will check the way we use our types. This is what we mean by strong statically typed. So now we've covered what a statically typed language means. Types are checked at compile time, and we've discussed how it can be useful. Now let's look at what we mean when we speak of a type system and how we can use a type system to obtain abstraction. So let's look at our user entity class, which recall is a table in a database. And we can see it has a constructor where it takes a tag type and it extends a class called table. Now we can see the table doesn't seem to have a constructor. It has these square brackets, and what goes in the square brackets are known as parameters. Now let's look at this column type. This represents a column in a database, and so you know from your previous database work that columns in databases can be things like numbers, strings, constants, timestamps. So these different things that can exist as column data in a database. So now we have these square brackets, and here we have an int, or here we have a string. This column is a type, and I can give it different types of parameters. Here I'm using two types, int or string. Let's quickly look at the definition of column. So here column is being defined with capital T. This is a parameterized type, or in Java we know them as generics. Let's look at our typical Java expression where we're using a parameterized or generic type. This is how we used parameterized types known as generics in Java. Here we have a method that's set up to work on many types. This diamond expression here with T is flagging to the compiler that generic or parameterized types are coming into this method, and they can be set up as the parameters there. And we return a strong type, string. Now let's look at the equivalent expression in Scala. Now in Scala we have functions, so we use the def keyword, and we flag to the compiler here in the brackets here the equivalent expression from Java there. So this is the input definition for the type, which we can use as a function parameter there. In Scala, after the colon we declare the return type as the strong type string. So here we have a parameterized method that can work with many types in Java. Here we have the equivalent functional expression in Scala. The key point here is we can provide abstraction in our program to reduce the amount of boilerplate. If we look in our code for our user entity class, we have one column type, but it can work on many other types. So we can have a column for ints, strings, other constants. If we look at the definition of a column type, we only have one column type, and by using these generic parameters or parameterized types, our column type can work with many other types. We don't need a new column type when we work with strings. We can reuse the column on many different types. So that's how we provide the abstraction. Now we could do a lot more than that. If we look in this Scala code where we are defining column, if we come down we can see type expressions like this. We seem to have an operational calculus acting on our parameterized types. So we have this expression. Here we have like a subtraction expression. So we seem to have these relationships between parameterized types. If we look up here, we seem to have an addition, and we have the Scala wildcard. What does it mean when we're using expressions like this on our abstract types? In Java, we have generic or type relationships, such as bound types. This is an expression for binding a type to a bound. Here, the parameterized type T extends A means that we can use any parameter for T that is a subclass of A. If it's not a subclass of A, we will get an exception. In Scala, if we have an invariant type parameter A, we can declare an equivalent expression to Java with this syntax. It's the same. T must extend A just as in Java. In Java, we use wildcards in a similar way. So our Java wildcard expressions map in an equivalent way to Scala, where instead of using the question mark, we use Java's wildcard, the underscore. Now, when we are talking about a type invariant parameter A, we can also look at our parameters and the ways our parameters are allowed to vary. So here we have bound this parameter. It's bound to be a subclass of A, so we allow a small amount of variation. Scala goes a lot further for bounds by implementing its concept of variance to define polymorphic relationships. The way that we can allow our parameters to vary has a complex relationship. If we look in the Scala code, we are starting to see some of these expressions in this code. This refers to these concepts of covariance and contravariance, and these set up the way the hierarchical relationships are structured, or the polymorphic relations. So if we have covariance, this is a direct correspondence. If A extends B, then the parameter relationship has the same polymorphic structure. For contravariance, then it's like a dual. Now, this quickly leads to very complex expressions, and this now has definitely left the realm of introduction to Scala, but we're pointing you in the direction that you need to go if you want to move into the more advanced conceptual framework of Scala. Now, types are something that we define and use. Types can be defined in classes and objects, and now we're introducing this new concept, a trait. So let's look at how a trait works inside a context of a type system. Here we are looking at the superclass for our column type. We can see that our column is an abstract type that is defined in this class column base. When we look at our class definition for column, we can see it extends this type rep. And if we look at rep, rep is flagged as a trait. Notice here we are defining two functions. We're defining their name, their parameter list, and their return type, but we are not implementing the behavior for the function. So this trait is acting just like an interface in Java, only the key point is we are extending it. So it's more than an interface. It's like a class, and in fact, if we so wished, we could implement the behavior of these functions in this trait. Now let's have a look at how a trait, like Java, allows us to achieve multiple inheritance. We have our column type defined in this abstract class, which takes its parameterized type. Can be int, string, whatever is the type that we want for our column in our relational table. And this column type extends the trait rep, which defines some behavior that's going to be common across all our column types. Now, every Scala class has a companion object. So this is the companion object for our column class. Now, objects don't have constructors, so we can't set up a parameterized type for this object. However, this static companion object column for our class column parameterized type extends a trait column low priority. So here we have a multiple inheritance scheme where our class is extending our trait rep, and our companion object for that class is extending another trait column low priority. So this is an implementation of multiple inheritance using traits. And here we can find that the trait column low priority is defining this behavior for column shape. So we have a complex interrelationship for types where we have parameterized types, and we define different types in traits and classes. So we can define a type with a class or a trait. Other subtypes can be defined inside these constructs, class, trait, or object. Then using parameterized types, we find them in classes, traits and functions, where they are acting as parameters in constructors or functions. Another important high-level concept that we need to understand when we work with types in Scala is what are implicits, what is meant when we have an implicit type. We will see the implicit keyword in Scala used in two distinct places. Firstly, we have an implicit type where we require a conversion of one type to another based on what is happening at runtime, similar to the Java keyword this, which implicitly defines the object in scope. We also have this idea of an implicit parameter inside a function. In this situation, we are asking for an inference based on the type for the parameter's behavior. Polymorphism is all about different behavior based on types. And in Scala, we have a very strongly defined type system. So when we are using polymorphism, the implicit keyword flags that the behavior that follows will be polymorphic based on the type. Let's look at this in the code. Now, remember, value is like final. So we are forced to use the implicit keyword here because we have a final variable that will be changing based on its type. This is a simple introduction to Scala's type system, and the implicit keyword is an important but difficult concept. We will try and illustrate it more in the next video when we look at object-oriented programming in Scala. Welcome to the Eduonics Introduction to Scala course. This is section 3, Scala as an object-oriented language. In the last video segment, we looked closely at Scala's powerful type system. In this video, we're going to look at how you can use that type system in what is known as object-oriented programming. And object-oriented programming and Scala's implementation of the object orientation model provide the developer with tools for designing composable, reusable modules. Composable means composition. That means that we can create a module out of many submodules to compose the bigger module. This we have found is essential for larger applications. In the last video, when we went carefully through Scala's type system, we looked at regular classes and abstract classes and traits. Along with these classes, we have this idea of a companion object that is associated with each class, and then we have the object keyword and a standalone object created with the object keyword that is a special type of class. Scala uses class-based inheritance for its polymorphism. It extends Java's inheritance module to provide for multiple inheritance scenarios using traits, which we looked at. When we have this powerful polymorphism, when we are writing distributed code, we need to have a handle on what is known as our mutable state. When we create a variable with the var keyword, then it can change. It's a variable. It allows for variance. But when we use the val keyword, we create an instance of an immutable object. Scala is a full object-oriented language. In Scala, everything is an object. Now, we said before that val is like static final, but Scala doesn't allow static class members. Instead, it provides this singleton construct called an object, and all members defined in an object are static. Let's look at some examples. This is the code from the first section where we looked at Scala success stories and Apache Spark. Here we have an example of a singleton object using the object keyword, and we can use this as an entry point for an application. To do that, we need to define the main method. Now in Java, we would have defined this main method as public static final, but in Scala, inside the object, everything is static. Now we are using the val keyword to create constant type objects. Here we are using the val keyword to create a static constant object, basic stats, and we're using the new keyword to create an instance of the class that we have defined here, basic stats. This is its constructor. We don't need to define an explicit constructor. We have an implicit constructor where everything is bound, so the method can freely call the constructor type parameters. To further highlight the constructor behavior for Scala, here we have a class, Scala product factory, that takes two integers as constructor parameters. This shows how we overload the constructors. So we have our initial constructor that will bind with the variables passed into the class through the parameters declared here. And then we have an overloaded constructor that we use with the this keyword, which will bind to our companion object. And when we create an instance of the class and we do not provide the second constructor variable, then we will call this overloaded constructor that will pass through the default value of 1 to the full constructor. So this is an example of the binding and the constructor behavior when we create instances of Scala classes using the new keyword. Let's look a bit more closely at a companion object for a Scala class. Here we have a class, Scala class, where we've defined a function. You can think of this loosely like being an instance function. We would call this function with an instance of Scala class. Now we have an object with the same name. You can think of this as being the bag for all the static attributes of Scala class. So here we have defined the method divide. This is like a static method for Scala class defined in its static companion object. Let's look how it works. Here we are creating a new instance of Scala class, and now we are calling its instance function just like we would call a Java instance method. We call the static divide method in the static companion object as you would call a static method in Java. So we have an instance and we call the function method with this syntax. Then we have a static companion object and we call the static companion object function with this syntax. So it's similar to Java, but at the same time very different. So we have these singleton standalone objects that are useful for entry point main method constructs. Then we have static companion objects that have the same name as the class. Then we have a different syntax. We have an instance function type syntax and we have a static function type syntax. Here we are in a public Java class with the public static main method of Java. This shows a good contrast with the way Scala handles static constructs. So in Scala, we create an instance of a class. We could use that to call what we can think of as instance functions. Then again in Scala, we have our static companion objects and we define our static constructs inside our static companion object. Whereas in Java, we use the static keyword. In Scala, we use this companion object for our static code. Let's look at traits. Now, traits are similar and often used like Java interfaces. But if you are coming from a language like Ruby, you will be familiar with this concept of mix-ins. We don't have mix-ins in Java. So traits are very different to Java interfaces, though they can be used in the same way. In Java, we use the interface to define the behavior of a class, but we must implement that behavior in the class. Traits allow a different approach. In a trait, we can, as well as defining the behavior, we can implement the behavior in the trait. This allows us to compose the behavior or mix the behavior into the class. So like a reusable component, and they can be stacked. We can have more than one trait mixing in behavior into a class. So this favors composition over inheritance. So let's look at this excellent design pattern. So to link the concepts into our first example, when we looked at relational mapping code for databases, let's define an abstract entity type where we have an ID and a name. And we're defining these properties in our abstract type. Then let's define two traits that define behavior. The first behavior is to export the entity to a JSON structure. The second behavior is to export the entity to an XML structure. So we have two methods in two traits. Export to JSON in the entity JSON trait, export to XML in the entity to XML trait. Now let's define a concrete class user. We are extending our abstract class entity because we want it to inherit the behavior of an entity for a relational database. Notice how we have a pattern here. We are declaring the constructed parameters for user, and we're giving the ID and the name, and then we can pass them in to the superclass constructor. This is how we would implement the super keyword in Scala. It's implicitly set up. So the pattern there is define our constructor, then pass the variables defined in the constructor into the superclass constructor. Now using the with keyword, we can mix in the behavior we have defined in our traits. So we just use a with for each trait, so we can have more than one trait by using more than one instance of the with keyword. Now we are not defining any behavior in the class, but we have a singleton object, runner, where we create an instance of the class, passing in values to the constructor, which will be passed to the superclass constructor. Then we call the trait methods on this instance export to JSON or export to XML. Now let's run our object runner that's extending app, so it doesn't need to implement the main method, and we will check if our polymorphic structure and our mixin traits are syntactically correct. To run this code, we will just run it in the Scala IDE, because in the IntelliJ setup that I'm using here, we can only run from the jar. So to save time, we've just created exactly the same code inside the Scala IDE. It's a bit harder to read because in IntelliJ we can increase the font size easily. Now I'm going to run my main object. If I right click, run as Scala application, and you can see its output. These methods worked correctly. The code is syntactically correct. So our polymorphic structure using our mixins with our traits and our constructor passing constructor variables through to the abstract superclass and defining no behavior in this class, we're able to inherit the abstract behavior and able to compose successfully with the traits as mixins. So this is showing object-oriented code in Scala using its new concepts. The final construct we will look at in our introduction to object-oriented programming in Scala is what Scala calls a case class. Recall we stressed in the previous modules when we write functional code and highly concurrent parallel code in general, then immutability is an important concept. So you can think of a case class as being like an immutable Java bean. Let's have a look at one in a context. Let's return to our original code we started this section off with, where we're using Scala to model relational mapping with relational databases. And we created a typical user entity and defined its columns. We could create a user case class to work with this entity, and this class could be used to store an immutable representation or view of this entity. This code here, we are defining a projection operator that will allow this data modeled by this class to be exported to this case class. Here we are using the option for the ID because we may not want to display the ID for the entity in the view, whereas the content for the entity, such as name and address, we obviously would want to display. So let's look at this case class in a context. The object data runner defines a relational mapping code block in Scala. Here we are using the typesafe slick object relational mapping package. Now we define a query, we create a database instance, and then we establish a session with our database. Here we initialize the users table. Then we insert some results into the users table. This code block prints out the results of our insert statement. Now we generate a select statement. Now we run our select statement. So here we are printing out each result of our select statement. So this is a result set and a standard printout of that result set. Now we are doing the same thing, but we are using the case class. Now our table is set up with a projection operator that works with the result set, and here we are catching that in an anonymous case class, and we are printing out the result here. So this shows how you can use case classes with the user entity table and its projection operator. This is the output when we run the code from the jar, and you can see from this output it was able to successfully work with the anonymous case class, which collected the results of the query from the projection of the data modeled by the entity from the database. So this shows how we can use Scala case classes with their built-in toString, equality comparison and copy methods, and they work like immutable Java beans with a few extra rules to do with the binding of their parameters in constructors, which you can read about here. Welcome to the Eduonics Introduction to Scala course. This is section 3, Scala as a functional language. Let's start by looking at some Scala functions and identifying what we can think of as functional magic. For example, there is no explicit return statement. If you are new to functional programming, this can be a bit confusing at first. Here we have a Scala worksheet in the Scala Eclipse IDE, and here we can see the output. So we have an object. In the object we are declaring a static function, add, which takes two integers as functional parameters and declares a return type of int and then defines the function behavior. So there's no explicit return keyword. And now the magic syntax increases on the next line. Here you can see that Eclipse is actually flagging this as an error because Eclipse is confused by this syntax. If we look carefully, we are defining the variable and initializing it with a function all on one line. Eclipse doesn't like that, but it's valid syntax because you see in the next line where we're printing it out, it's printing out the correct value free. So this is an example of some functional magic. If you are coming from procedural languages, you will think there are steps missing, but in a functional language, this is entirely valid syntax. As we saw in that code block, there is no explicit return statement. The value of the last expression is automatically returned, and Scala can also infer the return type of a function. However, for the function parameters, the type checking is strong. Scala will not infer the type of the parameters. Scala is a truly decorative language. Everything in Scala is an expression, something which returns a value. Rather than in procedural programming, where we program with statements, in functional programming, which is declarative programming, we program with expressions which you can think of as like rules. Let's look at how this functional magic can reduce the amount of boilerplate considerably in a pattern matching example. Here we have the keyword match, and there's some functional magic going on here which we will highlight. Now in this block we are using the case keyword to map integers, which are input parameter to strings, and there's no return statement. Now this is valid syntax. If we run this code, we see it's returning the correct value. Now the magic is happening here because there is no return type declared for the function, so the compiler is inferring the return type. Now if we were to add the return type, it would look like this, because we are returning a string. So this is equally valid syntax. So we can remove the return type and the compiler is capable of inferring it. So this is a good example because we have an object, so this is a static function, so we could call it easily. It's an example of how using the functional magic can reduce the amount of boilerplate considerably. No return type is declared and no return expression is declared. Scala does not have a switch statement, so we have this match keyword and this sort of code block that will act like a switch statement. So this is much more concise code than what we would write in a procedural language. The archetypal functional pattern is this technique called recursion. When recursion is used correctly, it can vastly reduce the amount of boilerplate and the use of resources by the application. Recursive function, when a function calls itself, is a powerful technique. So let's look at how we can use pattern matching to implement the archetypal recursive function factorial. Now this is a factorial function and we're using the match keyword, and if the match is 0, we return 1. The factorial of 0 is 1, and then we match on the wildcard anything else, and that will be the value that's passed in times the factorial, where we call it again, on that value less than 1. So it's just using pattern matching to implement recursion. Now the Eclipse compiler is complaining here. Now if we run this code, if we just run this code now, and it's saying, do you want to run the code even if there's errors, which is yes, and you can see it's producing a valid output. So this is valid syntax. If you look at Eclipse error, it's saying that it needs a result type. A recursive method factorial needs a result type. If we were to give it the result type, it would look like this. Because it's returning an integer, it would look like that. And the compiler is happy now. So the functional magic is the compiler can infer the return type. That's a good illustration of the magic that's happening behind the scenes. Now there's no return type, it's pattern matching, and it's a nice implementation of the functional syntax for creating the factorial function. And here we are calling it as a static function. Recursion is when we have a function that calls itself. When we have a recursive function, a function that calls itself, it's easy in other programming languages to get what's called a stack overflow error. And that's because those languages, when the compiler builds a code, is not able to do what's called tail recursive. That is, the compiler can convert the tail call to a loop, and that avoids the stack overflow. The Scala compiler can do this. So if you have a functional language, it's important it has that tail recursive ability to deal with recursive function calls. Let's have a look at what that looks like in code now. Factorial with tail is the new recursive code. And now we have this new variable configured in the constructor and initialized to one called accumulator. The accumulator is acting like a temporary storage and swap variable. So it swaps with the last value of n and stores the accumulated value in the expression. Here we can see that happening in the function call. So this works much more efficiently because the Scala compiler can unwind this expression into a loop. And we can see that efficiency now when we test this function against the non-tail recursive function. First, we will run the factorial with an impossibly large number. So the factorial of 30,000 is beyond the computer's ability to store. But will the function handle it? So if we run the factorial function on this impossible factorial number, you can see we have an exception here. We're getting a stack overflow error. If we change now to the factorial with tail, so we'll save this, clean the project, make sure we're running off the latest code. Now if we run the recursive tail version of the function, we get 0 because it can't possibly contain the value inside a long. We do not get a stack overflow error. This is the key point. The recursive tail function was able to unwind it into a loop and it didn't fail. But the factorial, the recursive function without the tail, gave us a stack overflow error. When we have this tail recursive intelligent compiler, such as in Scala, then we can safely use recursion. But without this, we are always in danger, if we have some small error or lack of understanding in our code, that we will generate a stack overflow at runtime. Now we will define higher order functions. These are simply functions that take a function as a parameter. So a function is a type in Scala. We will just have a look at a quick example. Here we have a square function, which just takes a single integer and computes a square. Then we have an add function, and it takes the function as a parameter defined here, where I have a handle for the function and this syntax for its input parameter and its output parameter. So this is a parameter handle we declare in the function parameters, and here we are using it in the body of the function. Now we could call these static functions with an instance of the containing object. So here we are calling the add function and passing in the square function as a parameter to the add function. So let's examine this syntax now. If we run this code, you can see it's syntactically correct. So we can declare functions as parameters this way. Another important technique in functional code is called currying. Now, often this will be stated as a way of transforming a function so it can be called as a chain of functions. You can also think of it as a type of functional decomposition. So let's have a look at a currying example. Here I have a function, very simple add function, just adds 2 integers. And now I have curried the add function. Notice the syntax here and notice the syntax here. So I first evaluate my x and then I evaluate my x plus y, which is the result that's packaged into the integer. So this is how I call. So here I'm calling the add, 10 for x, 20 for y. When I call it as a curried function, I first pass in the x value, then I pass in the y value. So let's check if this is syntactically correct. And I get the same value for both functions. So the syntax is correct. Notice when I'm using the higher ordered function, I need to define my input and output parameters for my function parameter. So it's a similar situation here when I'm defining the output of the curried function. The concept of a closure, or more correctly termed lexical closure, is important in functional languages like Scala. Now, a closure is simply a function which carries references to the environment in which it was defined. Here I have a function, and in this function I've defined a closure. So the return value here is a function that takes an int and provides an int. So this is the definition of the functional type, that is the closure, and this is the definition of the closure. And this function returns this closure as a function. So I would use this closure in a higher order function as a parameter. So let's see how that works now in some simple code. Here is my function that returns a closure. I've called that closure provider. And here is my higher order function that uses a closure. And here I've defined my closure type as f, and I simply print out the value of f acting on 2. Now I call my function closerUser and provide it an instance of closure provider initialized with 10. And when I run this code, it should print out 10 plus 2 as being the values for the closure. So this is an example of a closure. We do not have a handle for this function. We haven't given it a name. So a closure is also an anonymous function in this context. So there is no problem with returning anonymous functions or returning functions that have names by giving it a handle, as we are giving it a handle here. We can use it anonymously, or we can use it with a handle or a name. Functional programming is a topic in computer science in and of itself. This has just been a gentle introduction to how you can use functional concepts inside Scala as a functional language. So we pointed out what can often appear as functional magic until you get used to the syntax of the language. And we've gone through the various concepts, pattern matching, recursion, looking at how the compiler deals with recursion via a tail recursive loop unwinding performed by the compiler to make recursive functions safe so you do not get Stack Overflow errors. We've looked at higher order functions, currying, and closures, which are three really important topics along with recursion in functional languages. And we've looked at simple examples of those functions and checked their syntax. In the next section, we will look more at higher order functions and important higher order functions that act on collections. Welcome to the Eduonics Introduction to Scala course. This is section 4, working with Scala collections, lists, sets, maps and streams. In this video segment, we are going to introduce the Scala collections. The question is, what is a collection? And for this video, the answer will be any type found in the Scala collection package or its sub-packages. There are two basic types of collections, mutable or immutable. So we have the package Scala collection.mutable and the sub-package Scala.collection.immutable. Now, a collection at a high level you can think of as being some data type that can hold data. If you're coming from the Java world, then you're already very familiar with collections like lists, sets, and maps. The recipe that we've been emphasizing from the beginning of the course is Scala is an important language because it has this recipe for success in concurrent parallel code, functional types working on immutable collections. So the immutable collections are very important. Immutable collections, once they've created, cannot be changed, where a mutable collection can be changed. Now what we're going to do is go through an overview of the Scala collections and their associated packages and try and create a schema, a way to describe them and a way to understand them at a high level. At an introductory level, we can think about Scala collection package as being the root package. The types found in the sub-package immutable share the same interface as the root package. It's also important to remember, if you are coming from the Java world, the Scala interface or trait is very different to the Java interface. The interface defines the behavior, so you can expect the same behavior, but in the immutable package you have that guaranteed immutability. Because types found in the immutable package allow the underlying data to be changed, modified, hence allow side effects, they have this different behavior, so they must have this different interface. So this is a way to create a schema or a breakdown for the differences of the types found in the three packages collection, immutable or mutable. This graphic shows the types found in the root or collection package. Traversable and iterable are traits that define behavior. And then we have our sequence, set, map. Now the sequence is like lists if you are coming from the Java world. This shows the types found in the immutable package, and we see they are the same types at a high level. We have set, map, and sequence. We have more types implemented. They protect their underlying data once they've been created from modification. Now here we have an interesting collection. In Java, string is not a collection, but in Scala you can think of a string as being a collection of characters, and strings are immutable. Here we have the collections in a mutable package. We have the same high-level types. We have a different implementation of many of those types. For instance, with map, we have an implementation as a weak hash map. This is important to point out. The weak hash map's key values are more likely to be garbage collected than a normal hash map or a linked hash map. Also important to point out is the array buffer. This is what we use if we want to change the values of an array, and similarly for the string builder. We have our synchronized types in this package so they can be used in a safe way for concurrent operations, but those synchronized types come at a performance overhead. So this is a possible schema for defining the collection types in Scala. We have a root high-level type, and this will share the same interface and exhibit the same behavior as the types in the immutable subpackage. They share the same interface. But then we will find different behavior or different types in the mutable package because they allow this modification. An example of this is the buffer type. We don't find any buffers in the immutable package, but we have the string builder and the array buffer types defined in the mutable package. So this is a breakdown of collections. Quick look at how we can use the syntax. We have the traversable trait. Now the traversable is the top level API type or trait found in the root package, and we have implementations that share the behavior because the collections in mutable and immutable descend from the collection types in the root package. This behavior, this traversable behavior, will be available in the sub package. Here we can see how we can use the constructors. So here with the map, we can set up key value pairs in its constructor. So let's look now at using these constructions that we are showing here inside the Scala REPL via SBT, so we can get a more deeper understanding of what we're doing when we use the trait types to create instance of the collections. We have previously described how you install SBT. Once SBT is installed in a terminal, when SBT is on the system part, if we type SBT console, we can access the Scala REPL in an easy and convenient way. Once the Scala REPL comes up, if we hit Ctrl L, we can clear the screen. Now, traversable is a trait. So if we enter this expression, the Scala REPL tells us traversable int equals list 123. So we will just unpack this expression. When we enter traversable with these elements, the Scala REPL tells us that this is equal to a list, traversable being an interface or a trait that defines behavior. List is an actual type. And more than that, list is an immutable type. So when we declare an interface, Scala is going to back it up with a type, in this case the list. The key point here is that list is immutable. We declare a trait type or an interface type, and then Scala has to choose how it's going to implement that trait or interface type. By default, Scala is going to choose an immutable type. So let's explore what is this immutability all about. So let's have a look at some types. Let's declare a variable, muti, to be our traversable with these elements. Now let's declare a second variable, muti2. Let's declare that as a list. So now I have two variables. I have a traversable muti and I have a list muti2. Now let's call the variable muti2 1. Using this syntax and the index, I can call an element of a list. So I call the second element of a list. It returns int equals 2. Let's try the same thing now with our traversable type muti. And here we are seeing traversable int does not take parameters. So our traversable type, even though it's backed up or implemented by a list, still only implements a behavior of a traversable type. But when we use the list type, we get the behavior of the list type. So let's look at one more expression where we will try and set our variable, our list variable 1, to be the value 6. And now we're getting error, and it's saying the value update is not a member of the list. We can't update list because list is immutable. We're getting a feel for how these collections work. First, when we declare a trait type, it will be backed up by a collection type, and by default it will be an immutable type. But even though it's implemented by the collection type, it still has the behavior of the trait type. By default, immutable collections will back up trait types, and because they're immutable, we won't be able to update them. They protect their internal data structure. There are many other operations we can perform on list, but any operation that changes its underlying data is not allowed. Lists are immutable, which is good when we are working concurrently, and they're also easy to work with. Here is an example of an easy way to construct a list using Scala's concatenation operator, 2 colons, and also introducing an important Scala keyword, nil. Now, nil is a type that represents a list, and here it's acting as the basis operator to construct a list. So I'm concatenating the values 1, 2, and 3 to an empty list. So we can loosely think of nil as being an empty list, and you saw it was happy with the result. Now, if we leave off the nil and we just try and construct a list like that, Scala doesn't really know what to do with that because it has no base type. So nil is of type list, represents the entry point for constructing a list, and when we always use it at the end, we are concatenating to it, and so we were able to construct a list successfully that way. We can also use our list Connie if we like. So if we were to make Connie free and we were to put Connie at the end here, this should work because Scala knows to append these values to the list. So now here we have the new list. The nil is acting like the empty list. And so there are lots of good ways to work with lists in Scala, even though they are immutable. A set is a collection that's very similar to a list, only the key point is it won't contain duplicate values. It's guaranteed not to contain duplicates. So we create a set just like we create a list. So here's our declaration, identical to the list. So there's our set, and it's immutable. Now we'll create a second set, and see we have 2 duplicate values, 3, 2 3s. And when we create our second set, you see it only contains 1 element 3. A set is guaranteed to only have unique values. This can be very useful in collection operations. The array type in Scala is identical to the array type in Java. It is fully mutable. Here I am declaring an array of dimension 3. So I have 3 indices, and I'm able to set the value of any index to be what I want. So here I'm setting the second value to be 4, and you can see it's updated it to be 4. So the array in Scala acts just as the arrays do in Java, but we have some extra operations that we can apply to arrays in Scala. This is an example here when we apply this operation where we are appending and prepending values. You can see now our array has been transformed to an array of dimension 5, and we've prepended 0 and appended 4. So you can see the syntax here. Wherever the plus goes, that determines whether we're going to add the value at the beginning or the end of the array. When the plus is before the colon, this is prepending, and when the plus is after the colon, this is appending. As well as lists, sets, and arrays, an important high-level collection type is map. This is some syntax to create an instance of a map in Scala. In the constructor, we are passing in the elements of a map, which are key value pairs. Here, the key is A and the value is 1. The key types and the value types need not be the same. The key types must be unique, but the values need not be unique. Now, here we are creating by default an immutable map. We can always call for its value by providing the key to its get method. Now, what has returned from this call using the key to get the value is an option of type int. An option is what we use instead of the null keyword as found in Java. An option is a bag for a type that may or may not exist. If it exists, it's returned as an object sum containing that type. If it doesn't exist, it's returned as none. Let's formalize this important result. An option of type A container for an optional value. If the value is present, it's returned as an instance of sum type A, and that contains the present value for type A. However, if that value is absent, it's returned as the object none. In Scala, iterators work in a very similar way to Java. So here I'm using my previously created list, kindly to obtain an instance of an iterator. Then we can loop through the collection using the two common methods, hasNext, which if the list is not empty or there is another element to the list, iterate2 will return the value true, otherwise it will return false. We can always obtain the next value in the list by calling next directly on the iterator. As well as the iterator, Scala has a powerful collection feature known as views. Views produce a lazy version of a collection that's very memory efficient. Here I have my list, my immutable list, which has 6 elements. And now I'm creating a lazy view of that list. We can see it's returning a sequence view. Now a sequence view allows us to go forwards and backwards. So we could call any element of a list or get anywhere in the list lazily. So here I'm calling the 5th element of a list. There are many more advanced features of Scala collections to do with lazy evaluations and views and the other collection types that we do not have time to go into in this introduction to Scala course. However, in the next topic we'll move on to the important higher order functions that we use to work with collections. Welcome to the Eduonics Introduction to Scala course. This is section 4, working with Scala higher order types, map, reduce, aggregate and group. In the last video, we introduced Scala collections, how they are organized, what makes them different, how you make them, how you work with them in an introductory sense. In section 3, Scala as a functional language, we introduced this idea of a higher order function. Now, a higher order function is a function that can take another function as an input parameter. Scala collections are defined with many important higher order functions that we use to work with them. Now we're calling them higher order types. We call a function is a type in Scala. Scala collections have higher order functions defined in their types or their supertypes or traits. These functions will differ depending on the version of Scala you're using and the way the function behaves. In computer science and data science in general, we have this concept of higher order types that we use when we work with data, and these are maps, reductions, aggregates and groups. Now there are many languages that implement these functions. For instance, SQL has group.By. In this video we will look at how Scala implements these higher order functions for working with data. We will now quickly describe each one. Group is just a function that will bring the data into logical or sensible clusters. Map, not to be confused with the collection map, takes one set of data and produces another set of data with some sort of change to the underlying data. A reduce or reduction takes a set of data to a smaller set of data. A good example of this is the average function. If I have a collection of data, then I calculate the average value of that data in that collection. I'm taking the collection to a single number, the average. This is a reduction. Now, the aggregate function is more complex, but this allows us to arrange the data or collect the data based on some common value. Let's look at how this works. So we're working with higher order function. So let's define a first order function. is even that takes an input parameter of an integer and works out a Boolean expression by looking at the modulo with 2, and when it's set to 0 we return the value true. Scala infers the return value for the statement, so the return value here is a Boolean because this expression evaluates to a Boolean. Many Scala collections, such as set for example, have these filter functions that are higher order functions that take what's known as the predicate function. A predicate function will return a Boolean value. So in this context, our first order function is even is acting as the predicate for the higher order function filter not. This is working on a set collection. So let's look at this in the Scala REPL now. Here we've obtained an instance of the Scala REPL using SBT console as before. We enter our predicate function is even. The Scala REPL has now informed us that our function is even takes an input parameter of an integer and its expression evaluates to a Boolean. We will generate our set data. This expression here will return a set of integers -10 to 10 encapsulated in our handle for this expression, set1. So set1 will be of type set. Let's see if the Scala REPL agrees. So yes, it's an immutable set, and we can see it has the integers from -10 to +10. Now we can apply our filter function on the set. Now we have to be a little bit careful here. So firstly, we're calling this a filter function, but the function is labeled filter not. That's because it evaluates the not of the Boolean expression. So if is even evaluates to true, then filter not will interpret it as false. Every collection will have different types of filter functions, so filter not falls into the general category of filter functions. So this is a lambda expression. So what I've highlighted here is the input to the higher order function. So it's taking a lambda expression, which in itself is a function. Now this lambda expression is composed in part by our predicate function. So I goes to is even of I is the actual function that's going into the higher order function. So we are not strictly using our is even as the input parameter, but we're using our is even of part of the overall function, which is a lambda expression which is going into the higher order function. So let's look at how this works out now when we call this function. So when we call this function, it's selecting all the odds. So even though our filter function returns true when we have an even expression, we are selecting the odds of whatever the input expression evaluates to in a Boolean sense. We can use this as a filter function by putting our own not operator to act on the output of our predicate function is even, and this should obtain the even numbers. So we can work in both a filter and a filter not with the one filter not function. So in previous versions of Scala, set had a filter function, but in this latest version they've changed it to filter not, but you can easily remove a not by applying your own Boolean operator on your predicate. Now our filter functions are acting on our collection. Here we have our original collection set, where we have integers between -10 to +10. Then we apply our filter function, and we take our set and we output a smaller set. So in a way, it's acting a bit like a reduce. But then also we are taking one set to another set, so it's like a map. The important point is that we are not changing the underlying data. So when we map and reduce, we change the underlying data. With filter, we just select the data that we want from the larger set. So it's not really a map, it's not really a reduce, it's a filter. Let's look at how we can use the higher order map type. So now we no longer speak of predicate functions because we're writing functions that will transform the underlying data. So here we have a very simple function, make even, just as before, takes an int, but now we need to define the output parameter because we're changing the underlying data. Here we're multiplying it by 2 to make it even. And collections often have a map function built in, So here we are using it like we use the filter function, filter not, and we apply it to a lambda expression. So we're using the collection map, a lambda expression, and our own mapping type function that changes the underlying data. As before, we define our function. So Scala REPLs informing us our output type is an int. Use our syntax correctly. Now we apply the collection's underlying map function with a lambda expression that we've created, careful to use the correct syntax, and using as part of that lambda expression our mapping function, make even, which will change the underlying set data from the integers from -10 to 10 to the even integers mapped by multiplying it by 2. So we apply that function and we can see we have the correct output. So this is a mapping function because we have mapped the data from one set to another set. Now we will look at an implementation of the reduce type. Scala has a number of reduce functions. So reduce left acts from the first element working to the right. Reduce right works on the last element acting to the left. There are other reduce functions, types that are like fold or scan, that act in different ways. To keep it simple, we will just work with our reduce left reduce function for our collection. Now we must implement our reduction, which we have done in this function here. Now the redo variable that we are declaring here is a holding variable or a storage variable, and our reduction must take our collection to a single or constant value, if you like. So here we are just doing an adding reduce. So we are adding all the elements of the collection together to get a final constant result. And we're going to work looking at the absolute value when our collection data point is less than 0 or negative. Otherwise, we just add. So first we will define our function to make sure that it's valid, and yes, the REPL accepts it as a valid function. Now we will call the reduction on our underlying collection, and it should return a constant value, which it has. So we have reduced our set1, which is our integers, to a constant value. So we have taken a collection and we have output a constant, and that is a reduction. Now we will look at the group function, which acts a bit like the filter predicates. We need some sort of an expression that's Boolean that when it evaluates to true allows us to define a group. Now we're looking at the set of integers between -10 and +10, so we can break them down on their parity, whether they are odd or even. So we create two groups, an even group and an odd group. We create our Boolean expression that evaluates to false or true based on our condition, in this case parity, and we include a default case when it doesn't fall into our definition. In this case this won't be used, but it's good practice to define it anyway. So let's have a look at how this works out. We'll go to the REPL now. As before, we've defined our set of integers, which defaults to the immutable set -10 to +10. We will apply our group.By function to this set of integers. We store our result in this value parity, and we can see our result. We have our groups, so we have our odd set, we have our even set, so indeed our evens are correct, our odds correct. This is a powerful feature built into Scala collections. So we have reduction, group.By, filtering and map. What remains now is to look at the aggregate function, which is a level up in conceptual complexity. Now we will look at the aggregate type. When we are performing an aggregate, we collect input from various processes and we combine them together according to a set of rules. So when we perform aggregation, it's generally in a distributed context. The newer Scala libraries have what are called parallel collections. These are collections that have methods defined that utilize the number of threads or processes that are available in the system where the Scala is running. So when I have an expression like this, I have an instance of a collection, then .par calls for the parallel version of that collection, and then I call the parallelized function acting on the original collection. I have a seed parameter, which is generally the initial value for my accumulation function in the aggregation, and then I have two expressions which I need to define. The first is the sequential operation that acts on the elements of the collection, and the second is the way I combine the results of the sequence operation. First, I will define my collection, and so I now have my integers in a set. Now I will perform my first aggregation. I'm calling for a parallel function with .par, then I'm defining my sequence operation as being a product. Each element in my collection will be acted on with a product operator. So I'll go 0 times 5, then 5 times 10, proceeding through the collection, and then I am adding the results of my sequence operation for my combination operation. So I look at the output of this function, and you can see it's returned a large integer, so the syntax was correct. Now let's change the way we combine to subtraction. So now I am subtracting the results of my sequence operations in my combine operation. So now I'm getting this negative number. If I try this again, I could well get a different result. So this time I'm getting a different result. The reasons are there are many ways that these results can be combined. So this is a parallel operation. When the threads return, depending on which thread returns which value first, then I could have different values as a result of my combination. So this is an introduction to Scala's parallel collections and the aggregation type. This concludes our introduction to Scala collections and these higher order types, where we can map from one set to another set, reduce a set to a constant value, aggregate a set in parallel, or decompose a set into a group of smaller sets. Welcome to the Eduonics Introduction to Scala course. This is section 4, working with Scala function end types, closures, scope, and syntax. A sensible question could be, what is a functional language? What does it mean to say a language is functional? And the answer could be really simple, like the languages Groovy and Ruby that have been around a while, or emerging languages like Clojure. These are examples of functional languages. This is what a functional language is. Scala is a bit different, because Scala is an object functional language. So in this video, we're going to go into a little bit deeper how Scala implements its functional flavor. Scala is a fully object-orientated language. That means everything in Scala is an object and is an instance of a well-defined type. A function in Scala is an object and it has a type, and that type is the function type. This is what we can call a function literal. This is an expression where we are not declaring a type, but the Scala compiler will correctly infer the type of this expression to be a function type. When we have an expression like this where we have no definition of the function, just the expression, this is an example of what we call a function literal. Now, how is a function different to a static or instance method that we see in other object-orientated languages? Functions only depend on the given parameters, so the behavior of the function is determined by the input parameters and what we do with them inside the scope of the function. Whereas a method may refer to the internal state of the object that it belongs to, or the internal state of the class variables of the class it belongs to if it's a static method. A method is only a member of an object or a class. It belongs, or it only makes sense in terms of that object and class definition. The object itself is an instance of a type, but the method has no type, whereas every function has a type like any other type, be it int or boolean. This allows us to pass a function to another function, hence we can create higher order functions. So let's look at what happens when we put this expression in the Scala REPL, and how does the compiler infer the type of this function literal. In a Scala REPL obtained via SBT console, if I enter this expression, the Scala compiler infers it as being of this type, function2. Function2 is a type that belongs to a family of type known as function n, where n goes as 1, 2, 3, up to 22. The type of the function is function n, where n can be 1 to 22, and we decide what the value of n is based on the number of input parameters. Here we have 2 input parameters, so this is type function 2. If we had 6 input parameters, it would be type function 6. If we had 1 input parameter, it would be type function 1. Now we will go into this at a deeper level, look at why this is important other than the obvious fact if we have 1 input parameter as function 1. We will now seek to understand how this is the glue that glues the functional world to the object world in Scala. These function n types are traits. Like an interface with extra properties, we use them to define types. So there is no actual function n trait as such, but there is a function 1 trait, a function 2 trait, up to function 22 trait. So we could talk about the family of them together as function n. In this code block, I'm creating an instance of a trait. When I do that, this is creating an anonymous class. I'm using the apply keyword to define the behavior for this handle for the anonymous class. Now this apply keyword is the glue that's binding the functional behavior to the instance or the object. I'm creating an instance of a trait, so I'm defining an anonymous class. I'm creating functional behavior, and I'm binding the functional behavior to the handle for the function with the apply keyword. This is the glue that binds the functional world to the object world in Scala. And the binding is happening here, where I'm defining the types for my input and output parameters for the function. So the input parameters will always be the first definitions, and the output parameter will always be the final definition. If we enter this expression carefully into the Scala REPL, the Scala compiler is correctly interpreting this as an instance of function 1 type that has an int as an input parameter and an int as an output parameter. We can call it with the instance handle. This code block demonstrates how we can create anonymous instances of a function type and use the apply keyword to create the behavior, which we can then call with the handle for the instance at another point in our code. So it shows via the apply keyword how functions and objects are bound together in the Scala language. Now we will move on and we will look at how the compiler can infer more complex expressions that in a sense can be thought of as similar to this anonymous type we are creating with a trait here. That is what we call a closure. Now, when we work with closures in a fully functional language, we need to understand the following concepts. What is a free variable? What is an open term? And what is lexical scope? The question is, what is an open term? And the answer is, an open term is a function that contains at least one free variable. Here we have a function is less than, its input parameter is an integer, and its output from its lexical expression here is a boolean. Here we are binding the input parameter to the variable x, but there is no binding for this free variable start with element. A free variable is a variable that's not bound to anything. In the function is less than, x is an input parameter, it's bound to what I pass in to the function when I call it, but start with element is unbound or a free variable. Now this function I've defined is less than is defined within the lexical scope of the containing function truncate list. So I've highlighted the lexical scope. Truncate list cannot be considered to be a well-defined function until all its open terms are resolved, or another way to say this, until its free variables are bound. What will happen is the compiler must reach outside the scope of is less than to the containing lexical scope and try and bind start with element to something. So it's going to reach out and bind start with element to this expression here. And this is what's known as closing over, and because this must happen, is less than is what we call a closure. So we define a function, truncate list, that takes a type list of integers as its input parameter. It returns a type list because we are using this yield keyword here to yield the result of this for loop as the return value. When we define the function truncate list, we create a lexical scope, and within that lexical scope we create this closure is less than, and it's a closure because it has a free variable, is hence an open term, and that open term must be closed to become a closed term, and it does that by inferring from whatever scope it can to bind with something for the free variable. Now, if we did not have this expression here, if this expression was contained somewhere else, it would bind to this expression here. It will reach out through the nested containing scopes. So we'll look in its local scope first, and if it doesn't find it within the local lexical scope, it will reach out beyond the lexical scope of this method, closing over in an attempt to close this open term by bounding this free variable. And that closing out of the open terms is where the expression closures come from. Because this has a free variable that must be bound, is less than is a closure. Let's look at these expressions and how we can use them in the Scala REPL. Let's start with our closure and see if it is well defined of itself. So if we paste in the closure into the Scala REPL, we can see we are getting an error because it's not found. It can't find anything for this free variable. Of itself, this is not valid syntax. So then if we take the whole expression and put it in the Scala REPL, and we could see it's a well-defined function, function1. In the lexical scope, the compiler was able to reach out and bind this variable that it couldn't in isolation. Now that we have a function that contains a closure well-defined in the Scala REPL, let's generate a list that it can work with. Here we are generating list 1, which is the integers 1 to 10. Now, we want to truncate this list by creating a start value that's greater than preceding values. So now we will append to the start of this list the value 7 with this expression. So now we have list 2. We can now truncate the list with our function that contains a closure. So now you can see it's successfully truncated this list by chopping off all the elements that are 7 or greater. So we were able to successfully define our truncate function, which contained a closure in the Scala REPL, and use it to operate on a list. Now let's highlight issues to do with the closures binding for the open terms or free variables and immutability. Let's start by creating a new version of our function, truncate list 2, where we have an outer binding with an outer scope. So let's put this value into the REPL to see if it will work with the new scope arrangement. So we've created an outer scope for start with element, and now we will see if our truncate list 2 is well defined, and we can see it's well defined. It's able to reach outside of the local lexical scope of the function. So now if we call truncate list 2 on our list 2 that has the higher first value, and we can see it's working correctly, so we can bind to the outer lexical scope. So now let's look at the issue to do with immutability. So by default, especially with collections, Scala is always going to choose the immutable types. And here we've created our start with element variable as being immutable with the val keyword. Let's now make it mutable by changing it to the var keyword. So we will redefine our start with element type in the REPL. Now it's a mutable variable, and we will call truncate list2. It's acting as before. Let's change start with element. So we'll use the original start with element, 6 now. And now we will call truncate list2 with the changed start with element. And do we see a change in the behavior? No, we're not seeing a change in the behavior. We are still preserving that immutability. Now this is an issue we need to be aware of. By default, Scala is going to always work with immutable elements, and it will try and preserve immutability. But we need to be aware of when that can change, because in a pure functional sense, when we work with functions, we don't want side effects. If Scala was allowing the mutability of our start with element variable to change the behavior of the closure, then we would get unwanted side effects, and we break the important paradigm of functional programming, that is, functions acting on immutable values. This is our key philosophy, or the key paradigm of when we write code with Scala. So we have to be careful with Scala, because Scala is an object functional language. It's not a pure functional language. So we always need to double check and be making sure that we are preserving the immutability of the types that we work with when we are creating our functional code in an object-orientated functional language like Scala. In the last video, we looked at the higher order functions and how they work with collections. In this video, we've looked at the type of a function more closely, the relationship that glues functions and objects in an object functional language like Scala. We then extended our functional understanding of Scala by looking at this very important functional concept of a closure, its associated concepts of free variables, open terms, and lexical scope. Then we finally looked at the dangerous side effects that can occur when we work with closures, when the compiler tries to bind the free variable that we define in the closure. This winds up our introduction to the functional concepts contained within Scala. What we're going to do now is move on to the important concepts that turn up when we are working with concurrent code in Scala. Welcome to the Eduonics Introduction to Scala course. This is section 5, Java Memory Model and Scala Concurrency. In this course, we have suggested a good motivation for learning Scala is the need to be able to write concurrent code. We have stated that with the rise of multi-core CPUs and the breakdown of Moore's law, clock speed of the CPU is not increasing as fast as the number of cores in the CPU, that this gives rise to the need to write concurrent code. And we have learnt from experience that functional code acting on immutable objects is a recipe for success when implementing concurrent or parallel code. Scala is a JVM language. That means it runs on the Java virtual machine. That means when your Scala code is compiled down to bytecode, the Java virtual machine does not differentiate it from Java or Groovy or any other JVM language. Hence it follows that the artifacts that Scala employs to create its concurrency model are Java artifacts, or in particular Java virtual machine artifacts. And the critical artifact that we need to understand Scala concurrency is what's known as the Java memory model, or JMM. The Java memory model is difficult to understand, and it becomes more complicated when it runs on many cores. So here we have a single CPU with many cores, or a machine with more than one CPU, and we have a Java virtual machine running across shared cores or CPUs. Each CPU will have a cache and main memory. Now, when the CPU performs an operation on some memory that's in the cache, it won't be in the main memory until the cache is flushed to main memory. We have two different memory areas, the cache and the main memory. The state of the variable can be different in the cache to the main memory. When we run multi-threaded applications in Java, in the Java memory model, we have objects in a special area of memory known as the heap. And then we have threads that run in their own memory known as the thread stack. And the object from the heap can go onto the thread stack, be operated on, then be popped off the thread stack back to the heap. A thread acts on an object in the heap. Then a second thread acts concurrently on the same object. So what is the eventual value of that object? It can be inconsistent. This is compounded with where that object exists in the actual physical memory of the machine. Is it in the cache memory or the main memory? So what is the eventual state of that object? When that state of that object becomes inconsistent because of the action of the threads of the system on that object, then we speak of that as being a race condition. If we think of the state of our application as being the sum of all the states of our objects, then we can think of our application having a thread state that is consistent or inconsistent. When the garbage collector performs its garbage operation, it needs to have, or it assumes, that the operation of all the threads is in a consistent state. When it becomes inconsistent, the garbage collection can hang, pause, or fail. The end result of this is very buggy Java code. Unless we are writing well-constructed concurrent code, we will have garbage collection failures and inconsistent data. This is a big problem because to write well-constructed concurrent code is difficult. This means if we want to write good code that uses concurrency, whether it be Java, Scala, or some other language, we need to understand the system that our code is running on. Otherwise, we will make crucial errors. All modern operating systems support concurrency via what are known as processes and threads. A process is like a thread. In the POSIX or Unix system, we speak of a daemon thread. It is some sort of flow of computation that starts with a single thread, but that thread may spawn other threads or child threads, and that's a process, whereas a thread is often just thought of as a single thread. Now, Java has supported threads from the beginning, and the best way to create a thread is by creating what's known as a task, which implements the runnable interface. This is an example of that code. If you come from the Java world, you have probably written this code before. Now, starting with Java 1.5, we had this idea of what's known as the concurrency API, and that introduces this concept of an executor service, which is a high-level object we use to manage threads, and it includes this idea of what's known as a callable and a future. So this is how I create an executor service that will work with a single thread. Here I'm creating an executor service that will work with a pool of 10 threads. And then I submit my tasks that I create with my runnable interface to the executor service. And this is the preferred way to work with concurrency in Java now. Now the question becomes, how do I prevent the race condition? Java has a number of ways, but it all comes down to the visibility of the shared objects. Here I have two threads working on the same object. One thread can access the object, and while it's being accessed by that thread, I limit the visibility or prevent the visibility of the object to another thread in the system. And that's achieved in Java in what's known as a blocking or locking way. There's various ways I can lock down the object using the synchronized keyword, the volatile keyword, or creating an instance of what's known as a lock. When I put a lock on the object, then I block the object to the other threads. Now, the executor framework or the executor service allows me to get around this blocking and simulate asynchronous or non-blocking code with futures. So I create a thread with my executor service, and then I can call for the result of that thread at some future time. But really this is just a high-level wrapper over this basic lock or block mechanism that I achieve with volatile and synchronized, or I perform manually by creating my own locks. An important lock that we will run into later is this idea of a countdown latch. So this allows me to create a lock that has a time parameter, and I can call and increment the lock with the countdown method. So here, after I call countdown on this latch 3 times, that will remove the lock. So I have various mechanisms based on the visibility of the object that's being acted on over time by the threads in the system. And that visibility, which is achieved through blocks and locks, is what we call the Java memory model. The key point is it works through blocking access to other threads while one thread is acting on the object in the heap. And it achieves that blocking via visibility, via locks, which we can create manually. We looked at an important one, countdown latch, which happens to underpin a lot of Scala concurrency, which allows us to manually unlock based on certain parameters. Then we also have blocks, which we achieve with the keywords synchronized or volatile. The volatile block is especially important because it introduces a transactional idea that the write happens before the read. Any write operation on a volatile variable is guaranteed to act before any subsequent read operation, so we can have some transactional integrity applied to the variable being acted on by the threads. So with the volatile keyword, where we require that writes happen before reads, we are moving into the transactional world. And if you come from the transactional world as it relates to relational databases or other databases, then you understand this idea of an ACID transaction. When we are working with concurrent code, the atomic is the top level concept for ACID transactions. Our code is atomic when it's synchronized, where we avoid the race condition. Atomic is ACID in a transactional sense, where write happens or it rolls back to the last consistent state. So when we're updating a variable, if something goes wrong, we roll back the update uninterruptible. And this becomes important in Scala because Scala implements this really well. We have blocks of code, and when the writes happen, they happen in blocks, and while that write on a block of code is occurring, it can't be interrupted by any other task. So this idea of atomic, when we're talking about data and variables, has grown out of the experience with working with transactional databases and transactional systems in general. The idea is that if something breaks, we can roll back to the last consistent state of the system. This is the design principle to make everything as atomic as possible so we can achieve success in complex systems. By a complex system we mean not just a concurrent system where we have many threads or processes updating the data. We also mean where we have more than one core or CPU, and we have a fragmented memory structure where data is being updated outside of the heap in these cache memory areas. So this means that we need to introduce this transactional idea into our memory model, or this idea of atomic. And this is achieved in the Java memory model with the following rules. The lock rule, where we have a release before every subsequent lock is acquired, and the volatile rule, where we write to a variable before any read. So things are becoming transactional. We have this idea of a transaction where we are reading and writing in a well-defined or consistent steps, so the data maintains its state or the data integrity is not broken. Things are still failing in our Java memory model, and mainly it comes down to the complexity of the system that we are running on. As an example of this complexity, we can consider the garbage collector. What do we do about all these objects building up on the heap? We're not in a language like C++ where we can destroy the objects ourselves. We rely on this garbage collector part of the Java virtual machine. It turns out it requires that all the threads are stopped when it runs a Java garbage collection. The memory must be in a consistent state. Because things are becoming transactional, it's quite possible with poorly written code that your threads and your memory is not in a consistent state, and so this breaks your garbage collection. If you possibly run some poorly written Java code and you've seen it lock up the screen, freeze the desktop, then after a period of time it comes back and behaves normally, it's probably a garbage collection sweep that's broken because the memory and the threads are in an inconsistent state. Everything is evolving and some trends are emerging for dealing with the transactional issues. The previous models of concurrency basically matched one thread of execution to an operating system thread. Now we have this emerging idea of using this thread manager artifact, sometimes called a scheduler, and the scheduler sits between the operating system or POSIX threads and what appears to us as a thread in our code. A scheduler we can think of as a higher level abstraction for managing pools of threads. Since Java 5, we've had the executor framework, which allows us to declare a thread pool, so it's acting like a scheduler. Now, things have moved further. With Java 7, we have the fork join pool, which actually underpins much of Scala concurrency, and this is more than a scheduler. This follows because even though we are using it like the executor service, where we are declaring a max number of threads, when we run our threads, they are not actually operating system threads. What they are is fork join tasks, and now there's no longer a one-to-one relationship between the number of fork join tasks we create and the number of new operating system threads we spin up. Fork join task, you can think of it as being a lightweight program thread, and we can have more fork join tasks created than the number of operating system threads that we spin off. So this idea of a lightweight thread that does not necessarily correspond in a one-to-one fashion to a more heavyweight operating system thread is an important emerging trend that we can see has been exploited in the Go programming language. So here, a Go routine is a lightweight thread managed by the Go runtime or the Go concurrency scheduler. Here we can see in the Scala documentation how you create and use fork join pools. When you are running on an older JVM, Scala needs to fall back to a thread pool task support. So here we have a code example of how we use fork join tasks and fork join pools in Scala. So here you can see we have a fork join task support type that we configure with an instance of a fork join pool. These are the key points. We have a higher level type for managing pools of threads. You could think of it as being like a scheduler. It works different depending on the JVM we are running on. On an older JVM, we will be working with threads. On a newer JVM, we will be working with these lightweight threads or fork join tasks where the number of the lightweight threads can be greater than the number of operating system threads we spin up. So in the next video segment, we will go further into how Scala uses the Java memory model when we write concurrent code. Welcome to the Eduonics Introduction to Scala course. This is Section 5, How Scala Extends Java Concurrency. In the last unit, we looked at the Java memory model and we saw how the complexity of the systems that the Java virtual machine is running on, combined with certain limitations to the Java memory model, that things needed to evolve to meet the demands for concurrency in modern applications. And Scala has evolved beyond the Java memory model, and it relates to the atomic nature of the objects and the operations on the objects that we want to achieve, similar to what is known as ACID transactions if you come from the transactional database world. Scala, along with other functional languages, implements this idea of software transactional memory. At a high level, this makes sense because the system is becoming so complex, it's quite possible that when we want to update the data contained by a variable, which in the long run, any variable is just a section of memory, and in the Java virtual machine, that memory is the heap. When we want to write to that section of memory, because of the complexity of the machine that the Java virtual machine is running on, it's quite possible for that transaction to fail for a number of reasons. So just as we do in the transactional database world, we want to be able to roll back the transaction when it fails. Functional languages like Scala achieve this through what is known as STM. If you follow this link, you will see they will go through, in a more formal language, many of the issues that we went through in the last video for the Java memory model, and the way it's based on locks and the issues that flow on from that. As well as using the software transactional memory, Scala can use this concurrent framework, Akka, that implements concurrency using these lightweight artifacts known as actors, that's based on the Java memory model and the fork join framework, with the fork join tasks as the lightweight thread that underpin actors. Now we can read about the relationship of Akka actors and the Java memory model in this article from the official TypeSafe blog. They point out the key artifacts in the Java memory model that actors use to achieve a very efficient concurrency. So the first is this volatile rule, which they describe as the happens before rule. So this means writes happen before reads. And the second point is this idea about the internal state of the actor. It's important to realize that with the actor model, you don't get any guarantee that the same thread will be executing the same actor. We can understand this because the number of operating system threads can be less than the number of fork join tasks that we create with our fork join pool. We have this concept of awake on-demand actors that are not going to utilize an operating system thread unless they have work to do. So if they have no work, they sleep. And when they have work to do, they're reactivated, but this time they could well be on a different thread. Now this is complicated depending on the JVM that the Akka system is running on. If we are running on the older Java 5 concurrency, then we're actually using the real operating system threads, and we only get the full power of Akka when we run on the later JVMs with a correct fork join pool. Akka represents the best way to use the Java memory model to take advantage of lightweight threads and to create this non-blocking yet transactionally correct system. So let's look at some typical Akka code at a high level and start to identify some of the key issues and Scala syntax. The first thing is messages must be immutable. Now recall in Scala the object keyword defines a static class and the case class is immutable. So here we have an immutable static object which is perfect for a message. So we have two message objects, run and message. This is how we create an actor by extending from the actor type. Then we must implement its receive function, and here we pattern match on the messages to define the behavior. In this code we have two actors. We have a client actor, and in its constructor we are giving it an instance of a countdown latch, and this expression here, actor_ref. Actor_ref is like a this keyword in Java or JavaScript. It gives you a reference to the current actor object. In the destination actor, sender is acting in a similar way, only it's acting for the actor object that sent the message. Here, the instance of the countdown latch is working with the internal plumbing of the actor to signal to the system when the actor is finished. Here, this is like a finish condition for this interactive loop between the actors. This is the message operator. This keyword actor with this exclamation mark sends this message to the actor that will act on that message. When we work with Akka actors, we define an Akka system, and our actors belong to the system we have defined. In any actor system, all the actors defined in that system will receive the same messages, so they are loosely coupled via their messages. If in their receive function, their pattern matching is wired up to act on the message, then the behavior of the actor and the system overall will change. So it's a very simple system. The simplicity of it works well with software transactional memory, or STM. Scala's implementation of STM is a simplification because each transaction can be viewed in isolation as a single threaded computation. This is achieved through its implementation of what it calls optimism. Optimism is where we have multiple atomic blocks running in parallel. So we have many actors and they have code, blocks of code, and they're all running in parallel. But then we look at that as being a single atomic block, and it achieves that through what's known as a commit barrier. And when we consider this single atomic block, when we perform a transaction, if something goes wrong, we roll it back to the last consistent state. So we're going to look now at how we have that simplification, the optimism concept, how we can have these multiple atomic blocks in parallel do a transaction as though there was only a single thread. That is, we're going to try and understand the commit barrier in Scala. The commit barrier is like a synchronization, and it looks at all the transactions across multiple threads and creates a common barrier point. Once the barrier point is reached, all the transactions commit automatically. It's based or implements all of this with the countdown latch. As an example of how this could possibly work, here we are using the countdown latch in this actor to signal to the actor system that we have reached our finalized condition. Here we are approaching the commit barrier, and all our parallel blocks, we have multiple transactions. Say we have X transactions. Then we set our countdown latch with X. We progress through the transaction. After each transaction, we decrement our countdown latch. When all our transactions are complete, we then count down with our countdown latch so the lock is released and the code can continue. Let's look at how you would use this in Akka. So we have this idea of multiple atomic blocks running in parallel, and we want them to appear as a single thread for the memory transactions using the commit barrier. So the way this works out in Scala is first we have to define our commit barrier. We do that with our coordinated type. So we create an instance of a coordinated type, and then we create an aggregate of the parallel atomic blocks. So we gather the atomic blocks of the actors into a single atomic block where we define a commit barrier. Now let's look at an example of where you would use this. So this is a classic bank account example. We have an account and we can add money to the account or we can take money away from the account. Obviously we don't want any errors here, so we put this system of actors, so we have a transfer actor and an account actor, we put this into our coordinated atomic block. And so now when we have the transactions, the transaction will go through. If something goes wrong, it will roll back. So this is a classic example of where we would use the commit barrier, and this shows you how we use software transactional memory, how Scala extends the Java memory model, this idea of optimism, the idea of atomic transactions, and the commit barrier implemented with the countdown latch. We have looked at the need for concurrent code to fully utilize the multiple cores that are appearing in the modern CPU. If we want to fully utilize the resources of the underlying system, then concurrent code will help us to do that. And in the current systems we write applications for, such as mobiles, desktops, and remote virtual machines or servers, then we need to utilize all the cores on the CPU or CPUs. However, there are other applications where concurrent code is essential, such as application servers that need to establish thousands of concurrent connections with users. Developing the code to create application service that can create these connections has been one of the big drivers for the development of concurrent coding techniques. Another place where we need to implement concurrent code is when we create applications with a graphical user interface or GUI. Modern toolkits for creating graphical user interface have what they call the GUI thread, and we don't want to lock up the GUI thread, we want to keep it free. Now the GUI thread is the thread that's responsible for talking to the underlying graphical system to create the graphical widgets that you make your user interface out of. So if you lock up the GUI thread, then the application becomes unresponsive. So when the user is trying to use the interface, they find it doesn't respond because the GUI thread has been blocked or locked up. So this graphic gives you an idea. So we have some sort of a window with an event handler, and the user is trying to interact with the interface via events. Then we need to send a message. Now if we send a message on the GUI thread, then we could lock the GUI thread down until the message responds. But if we send the message on a background thread, then we keep the GUI thread free and the application's interface remains responsive. So designing applications with user interfaces is an area where we use concurrency not just to utilize the resources of a CPU, but is necessary for the application's requirements as per what the user expects. There's an application framework known as Scala FX where we can utilize the Scala language and its concurrent capabilities inside a user interface toolkit. This is the website for Scala FX where you can find the documentation and the source code. Scala FX is created with the Scala language based on the Java GUI toolkit Java FX8, which has evolved in Java to replace the previous GUI toolkit Swing. Here is some source code that creates a simple window with a rectangle that changes color based on mouse events. So here we have our Scala FX imports. Then we have a static object. It's extending an object that will initialize the GUI toolkit. Then we create a high-level window, and in its constructor we initialize some variable, a title for the window and the window's dimensions. Now we create some content for the window, and in this scene objects constructor we initialize some variables and we add the content. In this case it's going to be a rectangle, so the content is a type for the scene object, and we create an instance of a rectangle type. In the rectangle's constructor we initialize some dimension parameters and we initialize a fill type based on the action of a mouse hover event. If you are familiar with GUI programming, then you'll know this is a very small amount of code to achieve a lot of behavior. This follows both because Scala is an object functional language, but also it is more expressive with less redundant code than Java. Now reactive programming is code where we base it on reaction to events. It's a very strong paradigm for graphical user interface application design. It's asynchronous and event-based. When we have a functional language like Scala, then we can implement what is known as functional reactive programming. In the next video segment, we will go through how we can create functional reactive programs using the Akka framework and Scala FX. Welcome to the Eduonics Introduction to Scala course. This is Section 5, Functional Reactive Programming with Scala. In this video section, we will step through the Scala code that will provide us with the following learning objectives. First, to be able to set up actor systems that make requests off the main thread, such as a web request. Then set up an actor system where we have an actor that can call back into the main thread that is not an actor via a future. Then look at setting up code to create simple GUIs with Scala FX. Then set up in the code reactive event flows that combine GUI events with actor events and future callbacks. This is the code in IntelliJ. Project is called Scala Concurrent. This is the project structure, which we will just now look at in a larger view. The project is an SPT project, so the layout structure follows what we need for SPT. So in a project top level directory, we need a project directory where we have two configuration files, build.properties and plugins.spt. Then we have our source main Scala top level directories for our project packages, and we have a build.spt. So our key configuration files are build.spt in the top level folder. Then in the project folder we have plugins.spt and build.properties. In a previous unit we stepped through how to create an SPT project in IntelliJ, but we will just quickly review now. The two configuration files in our project directory are first build.properties, where we declare our SPT version. So this must match the SPT version we have installed on the system's path. Then in the plugins.spt we declare our plugins, and we are using the FatJar plugin that we used in a previous unit. Our build.spt is a little bit more involved than our previous build.spt we stepped through. We are importing the FatJar. Now we are declaring the name for the project, a version, an Akka version, and a Scala version. We set up our main class for our FatJar. Now we have our dependencies, Scala FX, Akka, and Akka needs logback. And our Akka version is pulled in from our Akka declaration. Then we have our local repositories, and finally this fork equals true. This creates a new JVM for when we run the Scala FX. In our top level package com.eduonix we have our entry point, which will be the entry point to our GUI application. We have a threadblocker.scala where we will develop our Akka code, and the threadblocker advanced.scala shows some advanced Akka code based on the threadblocker code. You can have a look at that as a self-study exercise. So let's achieve our first objective, that is to set up an actor system that makes a web request off the main thread. So in the file threadblocker.scala I have a class called simpleClientActor and an object called threadblocker. Let's have a look at the threadblocker. It extends app, so I can run it as a standalone application. Now on this line I'm declaring my actor system. I am defining properties, so I am passing in two values for the constructor. A remote, which is basically a URL of type string, a replies, which is of type actorref. This is like the this keyword for the actor instance. So I create a properties where I pass those values in, remote and replies. Then I use the actor system that I have created to create an instance of my client actor. Using the props method, I can pass initial values for my constructor parameters, remote and replies. I'm passing in null for the actorref for now. Notice here we will pass in the properties that correspond to how we have defined the constructor for our actor. Now that I have an instance of my client actor, I can give it some work to do by sending it a message that it's wired up to respond to. So this is my simple static object that creates this actor, gives the actor some work to do that will spin off a lightweight thread, and this object is a runnable object because it extends app. This is the Scala class simple client actor that has the constructor variables set up and extends actor. And this is its receive, where it will listen for message, and when it receives a message that it's wired up to respond to, it will do the work that we have created for that message. And here we have a function getURL input stream, and this is wired up with the constructor value for the URL. So we pass in the URL into this constructor value and we use it in this function, and it returns a response code. And if we want, we can return that value back to the sender. Now this is not an actor. So there strictly is no sender actor. So if we want to get this response code back into our main thread, we have some more work to do. Just for now, we can be aware that it's quite possible to pass messages back as well as receive them. Now we'll just go quickly through the code that makes the web request. For our function, getURL input stream, we only pass in one parameter, the string for the URL. Then in the other parameters, we create an initialize variables. This is unique to Scala syntax. Then we define our return type, and then we create the scope block for the function's behavior. Here we create an instance of a URL, then we use that to achieve a HTTP connection. Then we use that connection to get firstly a response code, and then we open up an input stream, and using the io.source package we can read the input stream and obtain the content of the HTTP response, and we print out both the content and we also print out the response code. So this is just standard HTTP code. These values are just standard HTTP protocol settings. Now we will run the code to check that our syntax is correct and that our code is valid. And so we have a response code of 200. So this is the output of this line here. So you can see this code is valid syntax. Let's move on now to our second objective, and that's to set up code that an actor will call back into the main thread via a future. Now we can send a connect message to our client actor, and in a lightweight thread it will make a web request off the main thread. But we want the result to call back into our main thread. So to do that we must create what's known as a future from the Java memory model. And we can do that easily in Scala by using this patterns type and passing in to its ask function an instance of the actor, the message we want it to respond to, and a timeout parameter that we can create with this syntax. Now at some future time our actor will call back, and we can use this type await and pass in an instance of our future to its result method and our timeout value. And when the Akka actor calls back from the future in response to the message, if it's less than this time value for that to happen, we can obtain the result in this response value, and we can print it to the console to check that everything worked. So we can run this code now, check that we have valid syntax. So it's running, and we want to see this actor response. There's our actor response. So our future that we created passed the message to the actor, and the actor called back into the await type in a time less than our duration time. So we were able to receive the response from the actor and print it to the console, and we can see the output here, and this is the HTTP response code, which is 200. Now that we have set up code where we have an actor that can call back into the main thread via a future, let's move on now and create a simple GUI with Scala FX. This object entry point is the entry point to our GUI application, and it extends JFX app, which makes it a runnable object, but also it has the Java FX GUI toolkit attached. Now we will step through the code at a high level. Firstly, we have these buttons. These are just buttons you would see on a screen that you can click on, and they are of type control. This action event type allows us to perform the reactive programming. Here we have our button, and its action is a click action. We define the behavior for the click action in this function onAction. And here we have an event variable, and this is a closure, and we can close over to obtain information from this event variable if we wish. So we can look at the sort of things we have that we can work with reactively. So we can find the source of the event, we can work with the target of the event, we can find information about the event. In this simple code, we are not working with the event, but it's important to understand the syntax here where we have a function, and inside the function from that closure, close over to obtain information from the event if we wish to use that information in the lexical scope of our closure. Let's run the GUI to understand better how all the code interacts. So we're running the GUI now, and this is what our GUI looks like. So when we click on the buttons, we are changing the label here. So from button 2, from button 1. You can see it's a very simple GUI. When we click on exit, we depart from the application. So we have the controls for our interface, 2 buttons that we interact with, an exit button and a label. Then we have a container for the buttons. We have a high-level window. We put the content into that window as the buttons container that contains our buttons and the lower feedback label. Now this high-level window is a stack pane. This stack pane allows us to stack controls one on top of the other. So that's our GUI code. So what we'll do now is we will wire up our Akka code into our GUI and fire off our Akka reactively from an event closure. So now we're in a position to wire our actor system into our GUI code reactively. So just as before, we configure our actor system, we configure our simple actor and create an instance and initialize it with the correct constructor values, create our timeout, and now in the onAction event, we create a future and then we have what's known as a blocking callback. This is the sort of way we need to set it up if we want to be able to report the results in a label. If we didn't have a blocking callback here, then we wouldn't see anything in the label because it would just probably throw a null pointer exception here. This code will wait until there's a response. It's not going to lock up the GUI thread, it will just lock up this action event. So we don't care if this action event gets paused, we just don't want the whole GUI thread to be paused. Call our future, wait for the response, and report the result here. So let's run the code now and check that our syntax is correct. So when we click on button 1, we're seeing the actor response callback. So 200 is the correct response code. This is very simple code. It's just to show you the idea of the utility of Scala. So we have an object functional language. We can wire it up with a GUI toolkit, and we can also wire it up with this very lightweight concurrent system known as Akka. The combination of a GUI toolkit, an object functional language, and a lightweight concurrent system is a very powerful recipe for making user interface applications. Just to summarize, we looked at the Java memory model to understand the terminology. The terminology to understand things like the concurrency API, what they mean by futures and callables. So we created an instance of a future here. So here we're creating a future, and here we are calling for its result. So this is directly using the Java memory model. Then we looked at the emerging trends and the use of the fork join framework and these lightweight threads, where we have a lightweight thread that doesn't directly correspond to an operating system thread. And then we looked at how we could create real practical Akka actors and use them in a real system like Scala FX to create functional reactive GUIs. This winds up functional reactive programming with Scala, and it winds up section 5. In the next section, we'll just concentrate on example projects written in Scala. Welcome to the Eduonics Introduction to Scala course. This is section 6, practical example 1, Scala microservice with Akka. In this video segment, we will explore further microservices in Scala and Akka. We will encounter issues as we develop a practical example. We will look at the solutions and the design methodologies employed by experienced and respected Scala developers. When we create our example, we will use Gradle as the build tool and try and show how it leads to high productivity. Here is an example where we can create the source directories for a Scala project, including all resources in test and the main source. So we run this task and it will create directories for us. Gradle tool allows you to use different JVM languages in the same project, and also Gradle as a build tool allows you to approach what we can consider to be a modular application design. We have previously discussed the concept of a microservice, which is a small functional unit of code that is independent, that implements a service. And instead of one monolithic application, such as a big web application server like Glassfish or JBoss, we can construct applications that are composed of many microservices. And Scala and Akka fit very well inside that application concept. Now, modular programming is a concept from computer science that relates to software design that is very similar. When we build an application out of microservices, we create these small code blocks that implement a service, and each one in its sense can run independently. Then we create our application as the aggregation of these microservices. In a similar way, we can use this idea of modular programming, where we create these isolated modules. So each module is independent from any other module, and it only wants to know enough about the other modules that it works with to be able to work with them and know more. But it's different to microservices because modules often cannot run on their own. Microservices and modular programming are an excellent fit. You will hear a lot more in the future about modular programming in the Java virtual machine development space because of the upcoming Java module system that will be implemented in Java 9. Here is a link where you can read more about modular programming, and here is a link where you can read more about the upcoming Java module system. We won't go too deeply into these high-level theoretical concepts, but we will, in our practical example, go through the steps to set up what we can call a multi-module Gradle project. The Scala modules that we will create in the Gradle project do not map to the concept of module as it's defined in computer science at the moment, but Gradle is moving to implement modular development. When we have Java 9 virtual machines, we will be able to create modular Scala Gradle projects, where the modules in those projects will fully conform to the software design of modular programming. This link here outlines in a very accessible way how Scala and Scala code can be created and applications based on Scala can be designed in this framework of modular programming. And even though it's going to be a while before we will see Scala running in Java 9 virtual machines, it's good practice to be able to incorporate this idea of modular programming. So when we create our Scala code, if we understand the modular programming design, we can create better Scala code. And what's interesting here is his schema, where he is saying the Scala object type is the high-level modular type. The trait is the module signature, and a Scala class is the functor, and a functor is like a higher level function. We could create our functions inside Scala classes and give our classes a signature with a trait, and then create modules out of objects that call these classes and create types based on traits. And that's basically what we do with Scala anyway. And so that shows how Scala is an excellent fit for modular programming. So let's look at how we can set up microservices in a modular fashion using Gradle. So this is my project outline. So here I have the name of the project, Scala Micro Modules, and here I have two top-level Gradle configuration files. Here in settings, I simply declare the names of the modules. So I have Akka Micro Client ML and ziputil. Then in my top level build Gradle, I set up this build script with this syntax. Then I have an all projects definition where I can give the group name, the version, and I can apply the plugins that will apply across all projects. So I'm making it multi-JVM language with Scala, Groovy and Java. And any top-level dependencies that are common across all projects can be declared here. Now in each module I have a build.gradle where I configure the dependencies and other configuration parameters that only apply to that module. So let's look at the Akka micro module. So we pull up its build script, and here it's declaring repositories, a main class name. The dependencies that are unique to this module will be declared here, and the tasks that will run for this module. So here we have a configuration task that will create the source directories via the Scala plugin. So we have the plugin Scala, and this will use that plugin to create the convention source directories for a Scala project. Then this fat jar task will create the runtime jar that creates the jar with the source code for the application and all its dependencies. And here we have a task where we can easily run the application from its jar artifact produced by the fat jar. This is the source code for the Akka micro module. Here we are using our object as our top level entry point for the code, and that's following our modular design. And we are creating an Akka system so we can work with Akka. Then we are creating a roots object here, which we are importing via our Socko dependency. Now, our Socko server allows us to create a server that we can run as an embedded process. So it's not like a top-level monolithic application server. It's a very lightweight server that we can run in an embedded context, and we can create request handler objects via Akka. So this roots object configures a root, which is a server REST endpoint. So here we have our main method. We create an instance of our server, and we configure it with its roots and its actor system. Then we start it up. Here we have created an Akka, which is a service handler, and it handles the endpoint we've defined in our root. When our embedded web server is running, it will have a context root, and by default it's localhost on that port. Then when we receive a GET request on context root, the web server by default will look for this type roots. So it has a root to pass the request to. And in here we will have pattern matching on those requests. So we have a case type GET that takes an instance of a request object and passes it out to an Akka system that's set up as web request handlers. And so if we look at our handler, it provides a date as a response to the request. So it's set up like a simple date service. If we look at the code for roots, we can see the root is an object with a function. And so this is following the modular pattern. So we think of objects as being modules now if we're inside that ML modular programming definition. So this is an embedded web server. By default has a context root, will pass GET requests to this Akka, and the Akka will respond with a date. So it's a simple service. Using Gradle, we can build our module. First we run our clean task, so we clean our module. Then when we run build, it will run through all the compilers. So it's run through the Java compiler, it's run through the Groovy compiler, because there's no Java or Groovy source code, went through them quickly, and then it went through the compile Scala, so it ran the Scala compiler on the code and produced our first jar. So we'll look at our first jar. If we go into the micro module, we go into the build, we go into libs, and there's our first jar. Now we will run our fat jar task where we will make the runtime jar. So now we're running the fat jar task. So the fat jar task depends on other tasks, which it's called. So it's called the compilers, and because we previously compiled, it went through quickly, then it ran through the fat jar. So now we have created our fat jar. So now we can use our server runner task, which actually runs the fat jar that we have created. So this is the server runner. So it's a type Java exec because we want to run a jar. So we need the fully qualified class name, and we need the name of the jar. So then we just simply double click on the server runner task. It's going to actually call the Java exec task and run the jar. We can see the server runner task. So now if we click on this link, it will open up a browser at the context root. We'll just pull this into view. So it's opened up a browser at the contact root, and our simple date service has returned simple date service. It's date service open parentheses and the date. So we can see here we have the date inside the parentheses. We have successfully built, packaged and run our Akka micro module using the Gradle build tool. As well as our embedded Akka server module, Akka micro, we have a REST client module. And if we look inside the build Gradle for the REST client module, we see we are pulling in this dependency for what is known as the Jersey client. Now the Jersey client is an implementation of what is known as JAX-RS. JAX-RS is a high-level specification for creating web services, and the JAX-RS client is a tool that we can use to configure a client to access any web service that implements the JAX-RS specification. So we can use this dependency to construct a Scala Jersey client, which we have done here. So this is our top level module, and we create an instance of a Scala class, and we configure it with a URL. So we're following our modular pattern. So we're using our classes and functions in our classes as signatures. So here we create an instance of the Jersey client builder. We use that to create an instance of a web target with a URL, and we have some standard what's known as Jersey code. Here we have a Scala implementation of it to create the rest of our client, which goes out, hits a server. We configure the media types. This could be JSON. For instance, we can have application JSON. Here we are just using simple text HTML. We hit the server, we get a result, we look at its response code, and then we print out the payload that's returned by the server. We can run our top level module and hit the Google URL to test that our code is functioning. So we're just running this as like a standard main class. So it's running now, and you can see it returned 200. So this response of the server result code was 200. That means everything is good. And this is the actual Google web page, which is coming in as the payload of the server response. Now I have changed my URL so that my Jersey client will hit my Akka micro embedded server. So now I use Gradle to quickly run the jar. So now my server runner is running on that URL. So now I return to my client code, and I run this as a main class. So it's running as a main class, and it's successfully hit my date service. So I was able to get my two modules to work together as microservices. So I have one module which is running a Scala embedded service. It's a date service, and it's using a Scala Akka service. Then I have another module where I have an implementation of the Jersey REST client written in Scala, and I can get these two modules to communicate via HTTP. So this is an example of how I can use Gradle and modular design to create multi-module Gradle projects that implement microservices. Welcome to the Eduonics Introduction to Scala course. This is Section 6, Practical Example 2, Scala Machine Learning, Apache Spark. In this video segment, we will go through what is known as machine learning with the premier Scala tool for all data analysis, known as Apache Spark. For this video, we will be running the code in what is known as the Spark shell. This is really just a Scala REPL that is configured with all the Spark dependencies for Spark's many libraries. This allows us to have the full functionality of Spark inside a convenient command line terminal. The easiest way to obtain an instance of a Spark shell is to download the Hortonworks virtual machine that comes pre-configured with Spark. It's known as the Hortonworks Sandbox, and you find it at this link. Now, there are numerous videos for Eduonics for Hadoop that go through all the steps of configuring the Hortonworks Sandbox for access on your operating system. We will not go through every detail of accessing the sandbox. If you are unable to access the relevant Eduonics training videos, then you can simply refer to the excellent instructions on how to use the sandbox on the Hortonworks website. This is the download link for the Hortonworks Sandbox. Just a quick introduction as how you access the sandbox and the Spark shell using the Hortonworks Sandbox. Here I have the Hortonworks Sandbox running as a virtual machine. And here I have the well-known PuTTY SSH tool. I simply set up a configuration. So I set my host name to be 127.0.0.1. I set my port to be 422222. Then I open, I log in, then I click open and log in as root. Then the password is Hadoop, H-A-D-O-O-P. And now I'm into the SSH terminal of the sandbox. Now, to access the Spark shell, I carefully copy this terminal command that's in red. I enter this into the terminal, and when I hit enter, I will need to wait for a while for the Spark shell to boot up. Now, in Scala code, I would create a top-level object and extend app, so I have a main method and can run this as an application. Then I would create a Spark configuration where I would need to set some parameters, like the name of the application, and set the master URL. Here I'm setting it to be as a local Spark runtime, and it's going to run on as many threads as it can find in the system. Then with that configuration, I would create a new Spark context. The Spark context is like all contexts. It's looking at the state of the system, the state of the objects, the runtime resources that are available for Spark. So it's a configuration object that we can use to access various parts of the Spark system, or sometimes referred to as the Spark kernel that we need. Now, the difference is in the terminal, we already have this Spark context configured for us. If we go Control L, we can clear the screen. Now, if we type SC, hit return, it will report that we have this object Spark context. So this is saying, yes, this SC is this object Spark context. So the Spark shell comes with a pre-configured Spark context that we can use to access what's known as the Spark kernel and the resources that are available to the Spark runtime. We access them. So this is our top-level system access object. Now we have our Spark context available in our Spark shell. We can use it to get system resources, and we can use it to make things. And two of the things that we will make is firstly what's known as a resilient distributed data set. This is a very important top-level object. Now, throughout this course, we've tried to emphasize what I have called the functional recipe, and that is pure functions that act on immutable objects, and this guarantees no side effects. And my claim has been that this recipe is the best way to write massively parallel code, and that's what we use Spark for. Spark is primarily a data analysis tool for working on massive data sets, and Spark, via its Akka subsystem, can spin off thousands of actors to process data using these resilient data sets. And when you act on an RDD to change its internal state or the values that it is holding, then it produces another RDD. The original RDD cannot be changed. The second type of object we create with our Spark context is known as an SQL context. With an SQL context, we can convert an RDD to act like a relational database. We can consider any RDD to be like a relational table, and we can query it with an SQL type syntax. One of the things that Spark's very good for is what's known as machine learning or ML, and you can read about Spark ML programming at this link. We will be looking at one particular aspect of machine learning, and that is regression. In particular, we'll be looking at how you implement logistic regression algorithm. Now, from Wikipedia, these images show at a high level the model that we are working with. So what I'm looking at here, this is known as a linear regression because it's working on a line. And here I have a distribution of data points that are roughly following that line. So I can talk about the linearity of this data, and I can make some sort of a statistical argument about the distance of any data point from the line and the probability of that data point being associated with the line. This is linear regression. Logistic regression follows a more exponential or logarithmic type curve, and this is more useful because this is working between two limits. Here I have an upper limit and here I have a lower limit, and so I can do a lot of useful things with a logistic curve that I can't do with a linear curve because of those limits. One of the things I can do is make this as a binary set of 2 points, the lower limit and the upper limit, and using that binary set that's composed from those limits, I can classify data, and that's something I can do with the logistic curve that I can't do with the linear curve. So for binary classification, where binary classification is useful, for instance, is classifying documents, text documents. Is this document a web page or not? So that's a model. So we will create a logistic regression instance in the Spark shell and use it to come up with some statistical arguments about the probability of data points. Spark is very popular at the moment because it makes implementing machine learning algorithms such as logistic regression very easy, and it does this via its pipeline that is composed of pipeline components, and you can read about these components here. The ones that stand out are training. So we have a model, but we don't really know what the model is. We don't have an equation, we just have some data. So training is the process of establishing a proposed model. So we look at the data and we say, okay, we think this is following a logistic regression pattern with certain parameters. So we set up some training data and we run our model with those parameters on the training data to establish our model. That is, when our model returns the desired results on data that we know supports those parameters for the model, we have our model acting correctly on our training data. Then we run our model on our real data, and based on the results of the model, we are confident when we make our estimations. Let's step through some code where we will use our pre-configured Spark shell Spark context to create and illustrate some of these concepts. We will create some resilient data sets, and then we will perform some operations on those resilient data sets to produce new resilient data sets. Here, using an SSH file browser, I'm looking in the root directory of the virtual machine where I'm running my Spark shell, and here you can see I've copied my data set I've used throughout the course, commercial banks, into the root directory. So let's create our first resilient data set by copying this line into the Spark shell and running that line. So we run that line, and the output is if we now just enter the address data So in the terminal now, we just put the value of the resilient data set, and it will tell us what the type is. So you can see it's creating an RDD of type string. Now I'm going to copy a case class that is a special immutable type of bean into the shell, and I will use this case class duplicate bag to work with this data set. So we copy this carefully into the shell. Now it has to go in as all one line. We enter that into the shell, and now you can see it's defined as class duplicate bag. So now I'm going to perform an operation on my data set that will create a new resilient data set, and I'm going to split the strings and then create a data set, have instances of this class type duplicate bag that will be configured by splitting the lines of string data in my address data resilient data set. So I copy this in carefully, and we'll see if that split works. Yes, and our split works. So if we look at the type for data frame, so we enter into the terminal just the word address data frame, will tell us the type, and you can see it's an mapped RDD. So RDDs are immutable. When we perform an operation on an RDD, it doesn't change the underlying data of the RDD, it returns a new RDD. Now we will step through some machine learning code. First we will import our SQL context so it's available in the shell environment. So we enter that import statement. Then we will create an instance of the SQL context from our pre-configured Spark context. Then we will use that SQL context instance we have just created to import more variables. So now we've configured our shell with an SQL context. Now I have my SQL context. I want to enter some training data. So I have a couple of case classes just as before. So I have a labeled document for my training data. So I generally use this convention of referring to training data as labeled and actual data as document. So I create a case class for my training data, and I will create a case class for my real data. Then I will create instances of my labeled documents or training data using this Spark syntax here. So we copy this into the shell to create our case classes. Then we create our training data. And we've successfully created our case classes and our training data. Now I create my pipeline components. First I must import my Scala dependencies and issue each line. So this is my first line, the second line in the shell. So now I have the imports. Now I create my tokenizer pipeline component, and then I create my hashing. So I have set up successfully my pipeline components. Now I'll move on to create an instance of my model, which is a logistic regression. So first I import my model into the shell environment. So I've imported the model, and now I create an instance of my logistic regression model with some initial model parameters for when I actually fit with the model or run the model. Now that I've created an instance of my logistic regression type, I can create a pipeline and use the pipeline and the training data in the labeled documents to create an instance of the model. So I imported the pipeline, I created the pipeline instance, and now I run the pipeline fit, and it's running through that code and it's fitting to the training data. So it's creating an instance of the model. Now that we have an instance of the model, we can create some test documents to test our model. So we could easily run our model on the real data, but we'll just create some in-memory data for now so that we can use our model. So we copy in, now run the prediction. And so now we're actually running our model. And you can see it worked out. So what we did was we set up a model with training data. We ran the model on some real data based on the probability argument, which is this score. We come to some conclusion about the data. Apache Spark is written in the Scala programming language. when we create Apache Spark code in Scala, we are creating native Spark applications. Machine learning and Spark have a big future, as shown in this website from IBM, where they are pointing out they donated their machine learning algorithm to the Spark community. The Apache Spark framework, written in the Scala programming language, has a big future. Welcome to the Eduonics Introduction to Scala course. This is Section 6, Practical Example 3, Scaling Deployment with Scala Concurrency. In this example, we're going to look at how you can use Scala to scale deployment, and we'll explain what we mean by that expression, scale deployment. So let's create a context for what we're talking about. Firstly, we have the application lifecycle. When you first set out on your journey as a Scala developer, when you write your Scala code and it compiles and runs, you will think, I've really achieved something. Now my application is ready. But this is far from the truth. When your application runs, it has many hurdles to overcome. For instance, consider something like a content management system that you will create and run on a computer where you develop the code, but will be used by a diverse range of users in diverse environments on different operating systems like Unix or Windows, on different platforms like tablets, mobiles or desktops. And your application has to be able to perform in all those environments and operating systems. When your application runs over time, it needs to be efficiently garbage collecting and managing its resources. So once you get your code to build and run on your own box, this is only really the beginning of your application development. So there's an application life cycle. So when we develop the code, we can use build tools and modular design patterns to create flexible applications built out of efficient, robust modules that can be reused. But what about deployment? What are the tools we can use for deployment? Well, we've seen with the Gradle code that we've been building, we can use the fat jar task to create these uber jars. But if you have some user that knows nothing about technology, if you give them an uber jar, they're not going to know what to do with it. You can't say to the chief executive financial officer, just run the jar in a terminal. That is not a professional approach to application deployment and development. So what are the tools that exist for us as Scala developers when we create our Scala application and we are at the deployment phase of our application lifecycle? Fortunately, because the Scala build artifact is a jar, we could take advantage of all the pre-existing Java deployment tools. The first tool to consider is what's known as WebStart, which uses JNLP, which is the Java Network Live Protocol. Here is a link where you can read about Java WebStart. It's a framework and it allows you to deploy an application from the internet via a browser. Now, the WebStart application is not viewed in the browser. What you do is you click a link in the browser and then a little while later the application is installed on your desktop with an icon or in your program menu. Click on the icon and your application runs independent of the browser. Another good option is Bedrock. Bedrock allows you to create an installer with an installer menu that is highly customizable, and you can do things like package your own Java virtual machine. So if you have a Scala application that can only run in Java 7, and there are many such applications, then you can install a custom Java 7 runtime with your Scala runtime jar. Bedrock is an excellent application with many other custom modifications you can do to create tailored deployment for your application. It's more configurable than WebStart, but it has a commercial license, so you must pay to use Bedrock. Now, beyond this, in the last application, when we looked at machine learning, there are other issues as well. When we are running massively parallel Scala code, and this is the big plus for Scala, that we can use the Akka system to create the very best concurrent code. This will often run in the cloud because businesses don't want to take on the cost of setting up clusters. They don't want to set up many computers that are networked together, they would rather run their data analytics as a cloud service. And here we can see some possibilities for Spark in the cloud. This is the Databricks link. Databricks are a company. It's well worth looking at their resources and their blogs. They specialize just in Apache Spark. Then in the last video we showed the huge investment that IBM have set up in Spark. So IBM have a dedicated Spark cloud service. And finally, Amazon Web Services with their Elastic MapReduce allow you to run Spark on an EMR cluster. So we have these options for running Spark in the cloud. Now that's fine if the data that we want to analyze exists in the cloud. But what if that data exists somewhere else? What if it is data that's generated in your company locally? For example, it could be sensor output from industrial machines. How do we upload petabytes of data to the cloud? This is the blocking issue, and this is the context for our application. We are now going to look at how we could create an application that uses the Akka concurrency to deal with the issue of uploading massive amounts of data to a cloud Spark cluster. We are creating this application as a module in our micro modules project, and we're calling this module ZipUtil, and its function is to zip up files it finds in this deployment directory. Now I only have 2 files here, but we could have hundreds of files here that could add up to gigabytes of data. And the idea is that it's going to scan through this directory, and every file that it finds, it's going to zip that file up. So it's a more efficient upload, obviously, because the zip files will be less bits to upload, so it will upload quicker. So if we can compress a gigabyte to 500 megabytes or less, then we'll be achieving a big efficiency gain for our application. If using compression, we reduce the amount of bytes we need to upload to the server, we need to balance that against the time it takes to compress the files. And this is where the Akka system comes in, because we can spin off Akka lightweight threads to do the compression. So we could compress 1 or 2 files per Akka thread, and this way we can gain the efficiency we need in time. This is the Gradle build file for our ZipUtil module, and here we have our main class runner. We have our dependencies. Now we're going to be working with streams and the Akka system, so we have an Akka dependency, and then these are the streaming dependencies. This is our source code for our ZipUtils. We have a utils runner object acting like the top level module entry point. We define our actor system we will be using. For this first implementation, for every file we find in our deployment directory, we will create an actor to zip that file up. So we need the zip output file, and we need the URL for the file that we will zip up, because it's a data source and we will output to a zip file. So we will create an actor for each file, and then this function sets up the actor properties for the actors that we will create with its output zip file and the URL of the file that we want to zip. Now, to find this directory, we first establish our user directory, and then we build our base URL for our source files via the user directory that we're in, and then we point it to the deployment directory. Now we create a directory for that URL. Then we use this loop here to do the following. First, we create a URL for our zip output. Find the input file, we find its path, and then we replace the extension CSV with zip. Then we use the file as a data source for our client actor. We create our actors in this loop. So here we are creating an actor for each file we find in the directory. We use our properties function, pass it the file and the URL for the file to make as a zip. And we also give it the name. So we need to give it a unique name. That's why we have the counter here. So each actor must have a unique name. So we increment counter so that each time we create an actor, it will have a unique name. So this loop creates the inputs for the actor and configures the actor. And then we also send the message to the actor to do the compress action for the attributes file and file URL that we pass to each unique actor for every file we find in the deployment directory. This is our ziputils actor. Here we have our constructor where we have the data source file and the URL. We establish the data source file as the zip file in the constructor. Then we have our actor receive function where we set up our pattern matching, and we call this function compress file, which takes a string which is the URL for the file that we will create as a zip file. Then we create an array buffer, and we create a file input stream using the input file as a data source. Then we have a counter and a read variable which we initialize. Then we create an output file stream that we chain with a zip output stream. So we use our file output stream in the constructor of the zip output stream, and these are the streaming dependencies that we imported in Gradle. Now we have a while loop. So while there is data that we read from the file, so each read operation will read in a chunk of data, and if there's no data left, it will return -1, and when it returns -1, we break out of the loop. For every read operation, we fill our byte array buffer with data, and then we can write that data to our zip output stream, which will end up in a zip output file. With the counter, we are reading the amount of data that we are reading and writing. Then once our loop is completed, we need to make sure we close our streams, and then we print out the amount of data that we read in the whole operation. So for every file in our deployment directory, we create an actor that will create those streams and create a compressed zip file. So if we have 5 files in the output directory, we will create 5 actors. Now remember, this does not correspond to 5 threads because an actor is a lightweight application thread, not an operating system thread. But the whole thing happens concurrently. We expect a big saving of time. So we can run our code to check that everything is correct. So it's running now, and we expect to see 2 zip files appear in the deployment directory. So if we refresh our deployment directory, we can see we have the 2 zip files, and if we make this bigger, we can see we had these amount of bytes in our read operation. We can go now into this directory and compare the size of the files to see what we achieved in terms of compression. So here this file is 992 kilobytes, and the compressed file is just 374, so it's a 1-to-3. This is, for a text file, we expect a big compression gain. So this is 1/3 of the file. So we would save a lot of upload time and resources by compressing this data. So if we had a gigabyte of text data to upload to a Spark cloud server, we could reduce that to 300 megabytes with this code. And because it's running concurrently, we expect it to happen quickly. As long as we have enough system resources to create a new actor for each file we find in the deployment directory, it shouldn't take much longer than if we were just compressing a single file. The Akka system is a very user-friendly way to create concurrent code that we can use for deployment tasks when we are creating big data application. Firstly, I hope you've been able to see that using actors is very user-friendly and a very easy way to create correctly configured concurrent code, whether we are creating an actor to handle a web request or we are creating an actor to handle some concurrent batch job. It's a painless and easy process. Secondly, I hope you've been able to see that we can use Gradle to create multi-module projects and design applications based on microservices, that Gradle is a great tool in combination with Scala for designing an application in such a way where we are using the object as our top-level module entry point, and then Gradle to configure the multi-modules and to allow interoperability between the multiple JVM languages and the other tasks that are available in Gradle, such as the fatjar task when we want to create a deployment artifact. And finally, I hope you can see the utility of the functional recipe, where we use functional code on immutable objects, and Spark has been able to capitalize on that recipe with its implementation of resilient datasets, where we have immutable objects acted upon by pure functions, so there are no side effects. This concludes the Eduonics Introduction to Scala course. Thank you for participating in the Eduonics Introduction to Scala course. Let's just take a moment to summarize what we have learned. During the course, we were introduced to the following top-level conceptual domains, that is, the Scala type system, the different types and how we can use them, Scala as an object-oriented language. We looked at how to create and use and the issues around Scala objects. We looked at Scala functions, closures and higher-order functions, and how we can use them with the type system and the object system. We introduced Scala concurrency by looking at its relationship with the Java memory model, and then at a practical hands-on level where we use the Akka framework to implement the different types of concurrency that we find in the modern application, using concurrency to handle web requests or using concurrency to handle batch jobs such as deploying big data sets. We looked at different ways we can build, package and deploy Scala applications using build tools like SBT, the simple build tool, or Gradle. We looked at typical use cases, that is, the type of problem that Scala would be a good solution for. Now, where would be a good place to go from here? Scala is what's known as a JVM language. That is, your Scala code that you write is going to run inside the JVM. There are big changes on the horizon for Java with the advent of Java 9 and the subsequent Java 9 based virtual machines. This will have a big impact on the deployment and runtime of Scala applications. These changes will be based on the concept of modular programming. We looked at this in the final section where we built quasi-modular code with the Gradle build tool. This would be a good study path to pursue concurrently with extending your understanding of Scala syntax.